Good morning. Let us start morning session. And first speaker is Professor Anna Cadoret. And the title of her talk is Degeneration Loci of l-adic local systems.
Yes. Thank you very much for the invitation. It's always a pleasure to be in Tuscany. First I will fix some notation for the talk. Maybe I will put them here not to erase them. So in my talk will be arithmetic. So I know the audience is quite large, but so K will be a number field most of the time. And I fix X a variety over K, a smooth variety over K, which I also assume to be geometrically connected. Yes, I'll try. Okay, sorry. Okay. Yeah, so smooth connected geometrically connected variety over K. So variety means, as usual, separated and of finite type. And what I'm going to fix and what I'm going to be interested in is, in the talk it was l-adic local system, but here it will be p-adic, but the same P is L. So it's a QP. So new P is a QP local system on X, by which, so if you are not familiar with this notion, so this is a local system in étale QP homology, you can think of it, and this is mostly how I will think of it in the talk, as a representation of the étale fundamental group of the base variety X. So pi1 of X here is a profinite group. This is the étale pi1, and it acts continuously on any of the fiber of my local system. So this is simply a finite dimensional QP vector space, and the representation is continuous. And so I will denote by pi, or sometimes pi of p, but later the image of the representation. And actually, because my variety is smooth, is normal and geometrically connected, the étale fundamental group can be split into a geometric and an arithmetic part. So this is the pi1 of the geometric fiber of X over K. And this is pi1 of the spectrum of the base field K, which is the same as the absolute Galois group, actually, of K. And each time you have a point on your variety, so a point in scheme, you can think of it as a scheme mapping to X. So the étale fundamental group is functorial, just as the usual topological fundamental group. So corresponding to this point, you have a morphism from the pi1 of the point to the pi1 of X. So the point is regarded as the spectrum of its residue field. So this is just a finitely generated extension of K. And so this is the absolute Galois group of this field. And this map here is always dominant. Only the image is open. So I can also, on this representation, look at the image of the geometric pi1, which I will denote by with a bar. So this is a normal subgroup of pi. And I have also, for each point, I have the image of the pi1 of small x mapping to the pi1 of capital X and acting on UP. So this one I will denote by pi1 with a small index x, and this is also a subgroup, a closed subgroup of pi. Okay, so these are going to play parts in the talk. And the my square, this is too small. So, and I will denote by similar later the Zariski closure. So G is the Zariski closure of pi, G bar, no, sorry, Gx, the Zariski closure of pi x. And I will denote by M, for monodromy, the Zariski closure of the geometric pi1. Okay, so we have in the end, 3 algebraic group we are interested in. situation in the z-axis. So G, M bar, and Gx are algebraic group, and pi bar and pi x are p-adically groups. Okay. So with this, I can define a notion of a special subvariety attached to my QP local system. So I'm going to say that a closed subvariety Z in X is special with respect to the local system if for every closed subvariety, sorry, closed irreducible. If for every closed irreducible subvariety Z prime containing Z, so if I denote by say eta Z and eta Z prime, the generic point of this variety, if the monodromy group attached to Z prime is the same as the one attached to Z, if we consider the connected component, then actually Z is Z prime. Okay, so it is, in other words, a special subvariety is a subvariety which is maximal for a given algebraic group, having a certain algebraic group as a monodromy group with respect to the QP local system. And so having defined special subvariety, this allows us to introduce some kind of strata. I like to, okay, this is fixed. How does a, sorry? I'm not sure to understand what you mean. Ça monte? Ah, okay, no, I'm just strong, not strong enough, sorry. And okay, sorry, I'm sorry. Okay, it's quite heavy. Yes, so having defined a special subvariety, we can also introduce some strata. So if you take any property of an algebraic group, you can just consider the strata, which I will denote like this. So this is just the union of the special subvariety such that the corresponding group. So I will. So if Z is a special subvariety, I will just denote by GZ the corresponding monodromy group. So this is just the union of special subvariety such that GZ satisfy the property. And perhaps the most important example, if you simply take the properties that of an algebraic group that the connected component be strictly contained in the connected component of G. So G is the image of the full étale fundamental group, maybe what I will call the generic image of the QP local system. Then what we get is, I will just denote it by X nu P. This is the exceptional locus of the local system. So this corresponds to, so the point contained in this variety are those where the group GX has dimension strictly smaller than the group G, or if you prefer from the p-adic side, this is the set of point X where the group PX is closed but is not open in pi. So this understanding this, so the main question I would like to address in the talk is what conditions on the local system could ensure that this exceptional locus is not Zariski dense in X. So not the whole, we cannot expect the whole exceptional locus not to be Zariski dense in X in general, even for a very simple local system. But the question is, if we look at the k-rational points inside the exceptional locus, and more generally, the set of points of bounded degree. So this notation here means I look at the close point. So those whose residue field is a finite extension of K. And I impose that the residue field be of bounded degree by D. So in general, for instance, over a field over a curve, if X is a curve, you may know that if X has genus larger than 2, it has only. What? So I was just mentioning that if X is a curve, you probably know that an X has genus larger than 2, the set of k-rational points is always finite. This is a famous theorem of Faltings, and I'm going to recall it later. But this set is not finite in general. So for instance, already for curve of genus larger than 2, this question of Zariski density is absolutely not trivial. And as we will see, this question, as you will see, this question is actually extremely hard. So I think currently it's, except for curve, it seems out of reach. We may make it more accessible by considering substrata of the exceptional locus and imposing some constraints. So those are becoming smaller, and the possibility that the Zariski of proving the non-Zariski density, might become more reasonable. So this is one main question, and another way perhaps to phrase it, or to a slightly different point of view, is to understand questions or problems maybe, is to understand how what the existence of our local system forces for the distribution of rational and integral points. So here, this cursive U means that I choose. So when you have a variety over a number field, you can always extend it to a scheme of finite type over an open subset of the ring of integer of your number field. For instance, if K is Q, you can always extend X to a smooth proper model over a ring of S integer. So this is what this cursive X means, and the U is this U. So these are the points which with good reduction, if you want, outside a finite set of places attached to U. Okay, and so the second point is a kind of very general question. So what I mean by the existence forces about the distribution, I mean, of course, namely study the intersection with the strata. So the second question is a very general and central problem in arithmetic geometry. We want to understand the set of k-rational points and integral points and varieties. And the first one is particularly interesting when we consider the fundamental example of local system, which are those we are arising from geometry. Or sometimes we call them motivic, by which I mean those which are cut out by algebraic correspondences on local system, which are higher direct image of the constant QP local system by. So you can take some twists. And here, this F is a smooth proper morphism. So the fiber, in that case, the fiber of the local system at X is the same thing as the étale cohomology group of the fiber, possibly twisted by G. So those groups are extremely important, and they contain lots of information about the variety Yx. And this information, so this comes with a representation of pi1 of X, and especially inside this, we have the action of pi1 of the base field. So this group together with the representation of the pi1 of small x contains lots of information about Yx, in particular the data of the algebraic subvariety is somewhat contained in it, at least if we believe in the Tate conjecture. And so if we can answer the first question, we can somewhat control the variation of lots of arithmetico-geometrical invariant in the family. And just an example of what, if we could answer in a dream, in a perfect world, if we could answer question 1, the kind of result you could obtain. So a typical range of application is when you take for F some kind of a universal family over a moduli variety. So if I consider AG, this is a moduli of G-dimensional principally polarized abelian varieties. If you really want to have a variety, maybe you have to add some level structure. And over this, you have the universal abelian variety. So this is my F. And if you consider the local system, which is the first higher cohomology of this universal family, assume you can prove is not the Iskidance. So this is my X. And actually, you should be able to, this is perhaps not exactly enough. You should be able to prove this not only for X, but also for the, so maybe I will write it like this to be more correct. It's not the Iskidance. Sorry. So if you can assume that the exceptional loci, the set of k-rational points in the exceptional loci, one restricted of the local system, one restricted to any subvariety of X is HE. then the kind of result you will get is the following, that there exists a band B which depends on P and G, such that for every G-dimensional abelian variety A defined over K, the set of the torsion, the P-silo of the torsion subgroup of the set of K rational points of your variety is bounded uniformly by B. Okay, so this is called the P primary part of the uniform boundedness conjecture for abelian variety. And if you could prove the same thing with a set of K rational points replaced by the set of points of bounded degree, you could replace the condition that A is defined over K by the condition that it is defined over a field of bounded degree at most D over Q. Okay, so these are long-standing conjecture in arithmetic geometry, and for the moment, this conjecture, for instance, the uniform boundedness conjecture, is only known when for elliptic curves in this generality. And the reason why it is known for elliptic curves, maybe I will mention it later, is that the moduli space A1 is a curve. Okay. So maybe I will state a very strong and probably completely out of reach conjecture, and then I would like to relate this conjecture, and actually weaker form of it, to more classical conjecture in Diophantine geometry. And explain why we could believe, at least it's not unreasonable perhaps to believe in such result. So I will say the main conjecture and the main, so it's really a dream, don't be is the following. So assume, and I'm going to define what it means, the local system is so I will explain this terminology. This is geometrically curved Lie semi-simple. Then for every D, the exceptional locus intersected with a set of points of bounded degree D is not the Euclidean in X. And so we say that so the local system is geometrically C curve L is Lie and S is semi-simple if each time you have a non-constant morphism from a smooth curve to X K bar. So this is phi, a non-constant morphism, and C is a curve over a smooth curve over the algebraic closure of K. And then you ask that the pullback of your p-adic local system to C is semi-simple, meaning that the corresponding, if you look at the corresponding representation of the étale fundamental group, so you not only ask that the representation be semi-simple as a representation, but that the Zariski closure of the image be a semi-simple group. So this is stronger. You don't allow a reductive group. So if maybe I wrote it like GC, you want it to be a semi-simple algebraic group over QP. Okay, and an example of GCLS local system are those arising from geometry. So QP local system arising from geometry are GCLS. This is a result of Deninger. Okay, so I would like to, so this conjecture, as I mentioned, is really too strong, but we are going to weaken it and at some point maybe get some results. So before stating some weakening of it, I would like to recall some classical conjecture in Diophantine geometry, which are somewhat behind the conjecture I would like to formulate for the exceptional loci and strata of attached to local system. So this is a very brief review. So I just need to introduce the notion of being of general type and of log general type. So a variety V over K is said to be of, so I put of general type and respectively of log general type if it fits in the following picture. So in this diagram, V1 is just, so the circle arrow are just open immersion. The middle arrow is just a proper birational morphism. And you ask that V2, that V3 be a smooth compactification of V2. So. And in the log setting, you ask that it be log smooth. So this just means that V3 is a smooth projective. And in the respective setting, you ask that the divisor at infinity be a normal crossing divisor. So if you don't know what this means, this is not really important. These are just a technical definition. And so the condition of being of general type is on the divisor, the canonical divisor. So you ask that the canonical divisor of the smooth compactification of a desingularization be big. And in the log setting, you ask for a Waker condition, namely that the boundary divisor plus the canonical divisor is big. Okay, this is and just an example. For curves. So if you have a curve, X is of general type, is the same thing as asking that the genus be larger than 2. And X is of log general type. This is the same as either you are of general type or you are genus 1 and you have at least 1 point at infinity, or you are genus 0 and you have at least 3 points at infinity. And perhaps a more striking way to define this is to say that the pi1 of the geometric fiber is not abelian. Okay. So with this definition, I can state the two main conjectures in Diophantine geometry. So there is one conjecture which is attributed to Bombieri-Lang, and they are very simple to state and very completely out of reach, completely impossible to prove for the moment. And the second one is attributed is due to Vojta, so we call it the Lang-Vojta conjecture. So the first one is for variety of general type. And the second one is for variety of log general type. So sorry, I'm going to erase the example. And it says that so if V is of general types, then the set of k-rational points is not Zariski-dense. And if you are of log general type, then the set of integral point is not Zariski-dense. So those conjectures are so they were formulated around the 86. There are very few known cases, as I mentioned. The most important ones are all due to Faltings. So for the Bombieri-Lang conjecture, he proved it for subvarieties of general type, of course, of abelian varieties. So in particular, this includes the case of curve, because you can always embed a curve into its Jacobian. So for curves, this was called the Mordell conjecture. And the Lang-Vojta conjecture is known for Shimura varieties of abelian type. Where it boils down to what was formerly called and often referred to as the Shafarevich conjecture for abelian varieties. So those two results are due to Faltings. This is why you got the Phil medal. Okay, so so actually, each of these two conjectures is somewhat yielding a different strategy or heuristic to attack the main question I have mentioned. So I would like to now to review them into to review them. And as you will see, so the Bombieri-Lang conjecture is yielding a kind of very general strategy, which is expected, of course, always in a completely dreamed world, to work for almost arbitrary local system, namely only those which is only the assumption that you be GCLS. And the second, the Lang-Vojta conjecture is going to yield a different heuristic, which is much focused on local system of geometric origin, because actually this second heuristic, so which provides for the moment much more unconditional result for higher dimensional variety, but it uses almost all the properties of local system arising from geometry. Okay, so I'm going to. So I will begin with the expected consequence of the Bombieri-Lang conjecture. So I erase the main dream conjecture. I will come back to it a little later. So expected consequences of Bombieri-Lang. So I'm going to state, so in this here, so NUP is an arbitrary QP local system satisfying, which is the QP, just the condition of being geometrically curved Lie semi-simple. And so the conjecture I'm going to formulate. So let us call it conjecture 1. It's exactly the same as the main conjecture, but only restricted to k-rational point. The set of integral points. So this curly X is so I have erased, but this is the model of X over a ring of an open subset of the ring of integer of the base. Thank you. So this is the same conjecture as the main conjecture, but I restrict to k-rational point because, as you noticed, the Monge-Ampere conjecture is for k-rational points, not for points of pointed degree. Okay, and I would like to explain why we can relate this conjecture to the Monge-Ampere conjecture. So the reason comes from the formalism of Galois category, which somewhat generalize what you probably learn about the Galois correspondence between open subgroup of the absolute Galois group of your field and finite field extension. So this formalism extends very generally to the étale fundamental group of a scheme and to étale cover of the scheme. Or if you are more familiar with topology, this is the same thing as the correspondence between finite indexed group of the topological fundamental group of the topological space and the the finite topological cover of it. Anyway, using this formalism to your QP local system, you can attach a projective system of non-connected étale cover of the base. So you have a tower like this. And so you are interested in understanding the exceptional locus of your local system. And this tower has the property that each time that you have a scheme mapping to X, the map factors through the exceptional locus, if and only if it lifts. So it lifts to a projective system of morphism along the tower. Okay, so in particular, you can apply this to Y, k-rational points, a k-rational point. And so this tells you that the set of k-rational points in the exceptional locus is exactly the image of the projective system of k-rational points along the tower. And so maybe you can guess what is what we expect to happen in general. And this is conjecture 2, which is a geometric conjecture. Notice that the condition of, as the terminology suggests, of being geometrically curved semi-simple is a geometric condition. It's not really on for the local system on X, but for the local system on X pull back to the algebraic closure of K. And so the conjecture is that for n large enough, this condition of being geometrically curved, least semi-simple should be enough to ensure that the every connected component of Xn is at least dominates a variety of general type. Yes, I should ask. I should complete conjecture 1. Actually, we can do the construction in such a way that we get something not only the non-Zariski density of the exceptional locus, but something which is very important for application, in particular, for instance, for the application to the uniform boundedness conjecture for abelian variety. We also get that the index of pi x in pi for points which are outside, which are co-rational, but outside the exceptional locus. So if you are not in the exceptional locus, this means that pi x is an open subgroup of pi, so it is finite index. But what we get is that you are not only finite index, but this finite index is uniformly bounded. And this is a kind of formal consequence of how you construct, if you are a bit careful, so you have a bit of flexibility in constructing these towers. And if you construct it in a clever way, you can add this to the statement of the conjecture. Okay, so this is so the problem of this heuristic is that, so I think that conjecture 2 is much more reasonable than conjecture 1, and the reason why conjecture 1 is not reasonable for the moment, at least, is that we know about nothing about the Monge-Ampere conjecture, and actually the community of algebraic arithmetic geometer is split into two: those who believe in the Monge-Ampere conjecture and those who do not. But this conjecture actually is also interesting independently of conjecture 1, because it also yields some application of algebraic geometric nature. So I'm not going to go into this. I don't have time, but it's important. It's interesting, and it's I think much more accessible. So maybe some non-case. So in all generality, so actually I worked a lot on this problem. So for dimension 1, when x is a curve, we could prove it with Tamagawa, and actually we could prove more. We could prove we prove the main conjecture in this setting. So this we could replace rational points by points of a bounded degree. The reason why is that for curves, this is specific to curve. You have a notion which is stronger than being of general type, which involve an invariant called the gonality, which is a maximal degree of a non-constant morphism of x to pi 1. And if you can prove that the gonality is larger than 2D plus 1, then you can prove that the set of points of bounded degree D is finite. And so what we prove with Tamagawa actually is that the gonality of those the connected component of these level schemes is going to infinity. And the only non-case, for instance, in for higher dimensional variety is when x is a product of two curves. So in general, for those kind of problem, passing from a variety to a product of variety is very hard. So, and this is a result I got recently. So I'm not going to tell a lot about the proof. So this is only conjecture 2 because so this is conjecture 1 and 2. This is only conjecture 2 because even for a product of for the moduli the scheme xn, which appear when you consider the base to be a product of two curves, we don't know the Monge-Ampere conjecture for them. They are of the form product of two curves modded by the action of a diagonal groups. So they're called product quotient surfaces. And even for product quotient surfaces of general type, the Monge-Ampere conjecture is not known. Because they are actually their Albanese varieties in general trivial. So they are somewhat the opposite case as the one proved by Faltings. Okay. And yeah, so the proofs are very also Abelian. So the only ingredient we use somewhat is the geometry of the base variety X and the data coming from the space of coefficients. So we have this group, the group which are involved, the group pi, pi x, pi bar, they are all p-adic Lie groups. And all the game is to try and understand how to estimate some invariant of the xn in terms of the representation. So typically, if you consider a curve, if you want to compute the genus of the curve, you would like to apply what is called the Riemann-Hurwitz formula, which computes the genus in terms of the ramification data. And this ramification data, you can actually estimate it by looking at the representation. And what is the key ingredient behind this are some result of some asymptotic bonds of Serre and Oesterle for the reduction, for the number of points on the reduction of modulo Pn of p-adic homogeneous space. So this is actually some p-adic, rather subtle p-adic geometry, which is behind those kind of result. So I would like now to just discuss briefly so the very strong form of the conjecture. So one reason perhaps to believe in the main conjecture I stated in the beginning is that at least for curve we are able to prove it. Another reason is that in general point of bounded degree D, you can think of them as rational points on the symmetric power of your variety. So maybe by some kind of formal construction, if you can prove, if you are in a completely dream world, you can prove conjecture one for every variety X, and you can prove it in particular for this with a certain local system built out from the original one. Maybe you can formally deduce the main conjecture from conjecture one. This is kind of just very general reason why maybe the main conjecture is can be tackled, at least considered. It's not completely foolish. And the other reason, maybe, so of course, this conjecture as stated are very, very hard because at least the arithmetic one, because of the Bombieri-Lang conjecture, but maybe we can awaken our goal by studying, as I mentioned, some substrata which are possibly more accessible. And at least there is one case. So actually, I haven't really defined those moduli variety, but what happens is that if you have, for instance, if you want to study whether the image of pi x is contained in a certain subgroup, the smallest the subgroup is, the smallest the subsystem of variety you will have to consider is. So the smallest the subgroup is, the most you have the probability that this is not the accident is higher. So, and the smallest possible group you can consider are those where pi x is or the hierarchical closure of pi x is a torus. So this is what I call the toric locus. So, for instance, you can consider the property that Gx is a torus, rather the connected component, because generality is not connected. So this is so I will denote this by Tor for toric. And so in that case, we have a much more accessible conjecture, which predicts that indeed the set of rational points of bounded degree in the toric locus should be not the Zeiss-Kidance. But this is not for arbitrary GCLS. This is for QP local system arising from geometry. Then, so the Manford-Tate conjecture plus what is called now the generalized André-Hort conjecture. Implies that X nu P, so the set of toric points of bounded degree should not be Zeiss-Kidance. And so very briefly, the argument, so I'm not going to give details, but the proof is that Manford-Tate plus generalized André-Hort reduced. So the reason why we need that the local system arises from geometry is to use the Manford-Tate conjecture, which tells you that instead of looking at the p-adic incarnation of your local system, you can embed your field into C and look at the analytification of your morphism and the singular local system attached to it. And for this, the toric point for our original p-adic local system corresponds to CM points for this analytic local system. And the generalized André-Hort conjecture is a conjecture about CM points. It's a conjecture in Hodge theory. And this generalized André-Hort conjecture allows to reduce the question to for CM points on Shimura variety. And for Shimura varieties, the set of the study of CM points is now much more well understood, and we have this very powerful strategy developed by Pilazzani, which seemingly eventually lead to the proof, the full proof of the André-Hort conjecture. And so we use part of the strategy, not the one using transcendental functional analysis, but the one involving the average Colmes conjecture. So it's a very so this average Colmes conjecture is a very deep result about CM theory, but with it we can prove this. Okay, so I don't have much time left, so I'm just going to say something very brief about the second main strategy or heuristic arising from the Langevin conjecture. So here's the main conjecture. So here, all what I'm going to say is for a local system arising from geometry. So, and the main conjecture, so conjecture 3, is that in that case, the set of integral points is not Zeiss-Kidance. So you notice that the conjecture does not involve the local system. This is not a mistake. And sorry, I forgot one assumption still. Assume the dimension of the monodromy group, the geometric monodromy, the M, is at least one, then the set of integral points is not the Esquidance. And the proof is sorry, not yes, the proposition is that, sorry, the Mandelbrot conjecture plus the Langvoita conjecture implies conjecture 3. And the proof is that, so by Mandelbrot, you reduce to the case of a polarizable variation of a structure. Then you can apply Griffith's algebraization theorem, which was recently proved by Brunebar, Baker, and Zimmermann. And this allows you to reduce to the case where the complex analytic period map is injective. Is injective at some point. And this, in turn, ensures that, sorry, the third set is that you have a result of Zhu, which says that then X is of a log general type. And then you can apply the Langvoita conjecture to conclude. And so we expect some very strong sparsity result for integral point as soon as we have the existence of a non-isotrivial QP local system on it. And what is nice in this, as soon when we consider integral points on a local system arising from geometry, is that now we have very relatively recently, I would say in the 10, 15 past years, there have been some tremendous progress on this kind of question, and there is now a a rather solid strategy to attack those kind of questions, which is due to Laurence Van Ketej, but I would say building really an idea of Kim. So I'm not going, I have no time to explain it, but one result for higher dimensional variety you can get is, so I cannot really prove the conjecture for toric point I mentioned, but a weak form of it under the following form. So there exists an infinite set S of a good toric prime, what I call good toric prime, for the local system, such that for each such prime as a set of toric point of k-rational point, sorry, of integral point of toric integral point is not the Esquidance. So here I erase the new because so when you come from geometry, so for each recall that you are of the form higher direct image of a constant shift, so you arise from a smooth proper morphism. So what I mean by an infinite set of prime, I mean that for infinitely many prime P attached with F fixed, I can prove this. The issue is that if we knew that those loci were independent of P when you have a local system arising from geometry, I could erase the condition on the set of prime, but for the moment, this is a conjecture. This set should be completely independent of P. This is a consequence of the Tate conjecture, but it's open for the moment. But so this is a wake form of the conjecture on toric point I stated before, but and this is I mean, what is nice with this result is that we have something for arbitrary variety of arbitrary dimension, and this is a consequence. So you have to run the Lorentz and Kettesh machinery. So this Lorentz and Kettesh machinery involves basically all the cohomology theory existing in characteristic 0. So we compare. We need to compare étale cohomology with crystalline cohomology using the decreased functor of Fontaine. We need to compare it to analytic cohomology, to a singular cohomology, sorry. And we also need to get a p-adic period map. And so for this, we need to compare it with the RAM cohomology and use the Gauss-Manin connection. So this machinery really involves basically all what we know about the cohomological incarnation of motifs. So it's a very somewhat a deep machinery, but it can produce in the end a very impressive result. And so I don't know if you know, but so the main breakthrough of Lorentz and Kettesh is that they gave a completely new proof of the Mordell conjecture using their machinery, and more recently they got more result of like the Shafarevich conjecture. So I will stop here because I have no time to elaborate on this. So.
Thank you very much. Are there any questions or comments? So that infinite set is positive density or?
So it's actually it's an image of a positive density set in the spectrum of the ring of integer of OK. So it's actually my base field is. So here I have something of positive density, and the image is a good toric prime.
Then actually plenty many.
Yeah, it's a huge.
How about the complement?
How
about the complement?
I don't. The complement? You mean the complement of the set?
Yeah.
I don't know. I cannot. I mean. Conjecturally, this is speak Z. It should be all the prime conjecturally. So hopefully I cannot prove that the complement is non-empty. Otherwise I would be famous. But because actually it should follow from the Tate conjecture that this is actually this work for all prime.
And what is a toric point?
So toric points is so I have introduced. So when I have my local system, so I have at X I have the image of so P1 of X is just the absolute Galois group of the base field because I take X here a k-rational point. So you can think of this as just a cohomology of the fiber. So this comes with an action of Galois because I take my fiber is a variety over K. So I have an action of the absolute Galois group of K, and I look at the image of that. This is what I denoted by X, and I look at the Zariski closure of this. So this is an algebraic subgroup. If I just write this vector space V, this is an algebraic subgroup of V, and the condition of being toric is that this be a torus. It is just some copy of GM, so abelian.
Algebraic torus.
Yeah, algebraic torus.
And how does it occupy such a point in X?
Sorry,
how does such a point occupy?
Oh, the
for XVP.
So the repartition of this, so for the moment, I can say that if you look at those which are integrals are not the incidents. And actually, so if you think of the, for instance, so if you, what is not true, for instance, is that if you erase this, they become the incidents in general.
You can erase this part. This part you can erase finally.
This one? So this one, so if I erase this?
No. Pass. Just you want to show just the integral point.
Integral points, so they are not the incidents. So this is what we can say. But
so question is how close to this original conjecture if you restrict to toric point.
You mean with k rational points instead of integral points? I think we are not so far because actually this is what I would like to prove this. Then I would like to replace this by this.
This is also.
And I guess this is not inaccessible. Actually, for Shimura variety, we know for Shimura variety. So the Pilazani strategy, Shimura variety, the Pilazani strategy tells you that essentially, so you have to be a bit careful, but roughly it tells you that this is not the incidence. And what the issue is that what my guess is that in general, a toric point, an integral toric point, perhaps after making a base field extension, is actually my guess is that that there exists a finite field extension of the base field, such that after performing this finite field extension, every k rational toric point is actually integral. So my guess is that this is essentially the same as. And the reason why comes from the fact that somewhat at the level of the action of Galois et al. Cohomology, we know that there are integral points, toric points are basically unramified outside the fixed set of place, which is independent of the toric point. And
thank you very much.
That's a bit technical.
So very close.
But not, we haven't reached it yet.
Are there any other questions or comments?
Yeah.
You mentioned that this variety has the fundamental group is not abelian.
Yes.
I think, for example, for variety of Cadoret type is virtually abelian, and for variety of finite type, they are kind of finite. So I'm wondering, in general, in higher dimension for this variety of log general type, are they the fundamental group are not abelian? Is that true?
So I'm not an expert on this, but I think the person who thought about those kind of question is Campana. If you're interested in this kind of issue, he has really formulated a certain number of conjecture relating the notion of being a log general type with some property of the étale fundamental group. But I think it's not so simple. I mean,
okay.
But I prefer not to answer because I'm not an expert and I'm not too sure about what is known and conjectured.
Are there any other questions or comments? So thank you very much again.
Thank you.
Second speaker today's morning session is Professor Christopher Deninger, and title of his talk is Dynamical Systems for Arithmetic Schemes. So please start.
Yeah, thank you very much for the introduction and for the invitation. I am kind of envious for you because you can follow these interesting talks, whereas I am at my home university and have a teaching week. I I followed some of the talks and I was really impressed by the level and depth and also how varied they were. So really a very nice conference. So let me start. I'll put this down. So I'll speak about dynamical systems. For arithmetic schemes. So motivation is recall the Riemann zeta function. It is defined as the Euler product over all the prime numbers of 1 minus p to the minus s to the minus 1 for real part of s greater than 1, and then it is known that it has an analytic continuation with a single pole at 1. And it is very important in analytic number theory. Now, for dynamical systems, we also have zeta functions, and I'm thinking of the real zeta function of a dynamical system. X0 phi t, where this is a continuous time dynamical system, so t is an R and phi t is then the homomorphism or diffeomorphism depending on the theory acting on x0. And so the real zeta function is defined in suitable situations as the product over the periodic orbits. So where gamma has a periodic orbit. And then 1 minus e to the minus s times the length of gamma, and then a certain signs, plus or minus 1, depending on the situation. And here L of gamma is the length of gamma. And this will converge if the real part of S is greater than the entropy, H entropy. Of course, for this to make sense, I mean, there shouldn't be too many periodic orbits. There should be so the number of periodic orbits with length bounded by a constant should be finite and not grow too fast and so on. So this is the real zeta function. Of course, if you compare them, it's clear that they are the same if the periodic orbits correspond to the prime numbers in such a way that the length of gamma is the log of p. And so you can think about the question whether there is such a whether there is such a dynamical system. Yeah? Those periodic orbits would correspond to the prime numbers in such a way. So I think many people have raised this question, and until now there had been no satisfactory answer. Oops, sorry. So, but even more generally, if we are given a system of Diophantine equations, pi1 to pi n, so polynomials over z in variables x1 to xm, we can look at the finitely generated ring quotient of the polynomial ring by, x1 to xm, by the ideal generated by these polynomials pi1 to pn. And also in this situation, there is a zeta function attached to such a ring as follows. So it is known by an old result of Hilbert that the residue field R0 mod M0 of the maximal ideal M0 in R0 is finite. Residue fields of these finitely generated rings of maximal ideals are all finite. And one defines the norm of the maximal ideal to be the number of elements in this finite field. And this is a p power for some prime number p, because finite fields have this property. So for example, if we have no polynomial and no variables, then we're just dealing with the ring Z. R0 is Z. The maximal ideals will be those generated by the prime numbers, and Z mod P is the field Fp with P elements, and its norm, the norm of P, is then the number P. So now we look at the something called the Hasse-Weil zeta function. Only one. It is again an Euler product, zeta of this ring. It is now the product over all the maximal ideals, M0, 1 minus the norm of M0 to the minus S to the minus 1. And one can show that for a real part of S large enough, in fact, greater than the Krull dimension of this ring, this function will be holomorphic. And it is a conjecture, but it's not known to, in general, to have an analytic continuation. So this generalizes. So this generalizes the Riemann zeta function, in which case we take R0 equal to Z, or the Dedekind zeta functions from number theory. So these are zeta functions which you attach to an algebraic number field. And the zeta functions of elliptic curves. All these are special cases, and so on and so on. All these are special cases of zeta functions that are considered in arithmetic. There are many conjectures. So there are many conjectures. For example, these Hasse-Weil zeta functions should have a meromorphic continuation. Meromorphic continuation to all of the complex plane C with some poles. Yeah? Of zeta R0S is expected, but not known in general. So if you write down some random polynomials with integer coefficients and form this ring R0, then it will certainly not be in the class where anything is known. The things that are known are about certain very symmetric, very structured spaces like Shimura varieties, elliptic curves over Q now by work of Wiles, and such. So there's meromorphic continuation, and there's even a Riemann hypothesis hoped for, which in this generality would say that the zeros and poles occur only for real part of S a half integer. So even for the Riemann zeta function, this is not known. And this is a generalization. So in arithmetic, one is not only interested in the Riemann zeta function for the study of prime numbers, but also one is extremely interested in these Hasse-Weil zeta functions. All of you might have heard of the Birch-Smith and Dyer conjecture, which concerns a certain behavior of the Hasse-Weil zeta functions of an elliptic curve. So, and it is very difficult to prove things about this. Nowadays, approach is using the Langlands program to write these Hasse-Weil zeta functions as a product of automorphic L functions, if one can, and then try to study the automorphic L functions. And for analytic continuation, the known cases, this works well, but this works only in special cases. And as far as Riemann hypothesis is concerned, nothing has been proved. So I have a long-term project to realize Hasse-Weil zeta functions as real zeta functions of some dynamical systems, and then explore the analysis, topology, and geometry of dynamical systems to prove something. And so for many years, I have been looking for a dynamical system, but not found anything. But recently I found something, and I want to describe it today. So let us note that Hasse-Weil zeta is equal to a real zeta if, as above, the periodic orbits correspond to the maximal ideals, and the length of the corresponding orbit would be the log of the norm of the ideal. So if you're looking for a dynamical system, this is what we want. Now we can be more general if we switch to algebraic geometry language instead of rings. And so we look at the scheme, the spectrum of R0. So this will be a scheme of finite type over spec of Z. This is now what we're looking at, schemes of finite type over spec of Z. Then the ideals, the maximal ideals, they correspond to the closed points. Oops. Small x0 in x0, the so-called closed points. Yeah, the singleton set consisting of this point is closed in the Zariski topology. So that's a different way to say these things. So I also want to say that there are more general reals, zeta functions, more general real zetas. If the periodic orbits are not discrete. But for example, in Hamiltonian systems with invariant tori, they come in compact packets. Yeah? And then to make a real zeta function, this situation one needs to look at fuller indices. And then in this way, one can still get a real zeta function and prove properties in suitable situations. So in the above picture, we had the correspondence, the closed points or maximal ideals should correspond 1, to the prime to periodic orbits, but they are actually more general reals. And for the dynamical systems that we will construct, the situation will be like in this more general situation. So what we do today is I define a factor for you, a factor from, on the one hand, normal schemes x0 of finite type over spec of Z.
Excuse me, can you
Yes.
hear me?
Yes, I can.
I have a question. So
Yes.
I'm wondering, when you say this Hasse-Weil zeta function and the rules zeta function, and the periodic point is kind of related to the maximum ideal. Well, what is the morphism? So this periodic orbit, what is your map?
A map to do what?
because you have this periodic orbit, then I'm wondering what is your map, or just the.
We have a map. We have an R action. My dynamical systems are continuous. So just the additive group of real numbers acts as time, and we look at the orbits, the closed orbits, and then we take their length, their period, and then we can form a real zeta function. And what we want to do is, we have not done it yet, in this talk. What we want to do is, if we are given a ring of finite type or a scheme of finite type, then we want from this to construct a dynamical system whose real zeta function will be the Hasselbalch zeta function of the scheme. This is what we want to do. This I will explain how to do it in this talk.
Okay,
I have not yet done it.
Thank you.
So this is the project for today. I want to define a functor for you from normal schemes of finite type over Z to connected topological dynamical systems x0 phi t with some properties. Properties should be that the closed points should be related to the periodic orbits. So this is what I want to explain, how this can be done. And so we need some ingredients. First ingredient is the rational bit vectors. Rational bit vectors. So if we are given a commutative ring, then one can form the so-called big bit ring. It is the following ring of formal power series. It is formal power series over A with constant term 1. This bit ring. And the addition is like this. So I write it with a strange plus because it's not the ordinary addition. The addition is the multiplication. Now, if you have two such power series, we multiply, the constant term stays 1. This is the addition. The multiplication, I will not explain. But there is a multiplication which turns this gadget into a ring. And it's not so easy to describe it, but you find it in the literature. Now, these are formal power series. Now we look at a certain subring, the rational bit vectors. This is the subring of rational functions. Quotients of polynomials whose constant term is 1. They live inside, and it turns out it is really not only a subset, it's a subring. I mean, the addition of such rational guys is by definition their multiplication. And if you multiply two rationals, it stays rational. And for the product, it's not so clear. But anyhow, it is true. And there's another way to look at rational bit vectors, which is better, Almquist. It was introduced by Almquist. And he established the following isomorphism. Look at, we take this is just for background. We take the category whose objects are finite rank projective modules together with an endomorphism. We call it like this, End A. And we take its K group, Grothendieck K group, and inside there are the finite rank A modules with a 0 endomorphism. And this can be identified with the K0 of the ring A, and we divide it out. And this quotient is isomorphic to the rational bit vectors of A. And this is the right way to think about the rational bit vectors, or it's a better way, because now you can see multiplication, addition and multiplication. So an element in the K theory will be a formal difference of an isomorphism class, or of isomorphism classes of pairs consisting of a finite rank projective A module V and an endomorphism phi. And what does this go to? Well, we send it to the characteristic polynomials. So 1 minus t times phi acting on V divided by 1 minus t times psi acting on W. Now, Almquist proves this is an isomorphism. Now, on K0, the addition comes from the direct sum. And if you take the direct sum of vector spaces with endomorphisms and look at the characteristic polynomial, then you get the product of the characteristic polynomials, which is the addition on the rational bit vectors. And also, the multiplication on K0 is induced by the tensor product, and this will exactly correspond to the multiplication on the rational bit vectors, which we did not explain above. So that's a good way to think about these things. Now, there is some extra structure. This ring of rational bit vectors has Frobenius endomorphisms, which commute, has commuting. They are called Frobenius. Endomorphisms. F nu for nu greater or equal to 1. And this theory of bit vectors, you always have Frobenii. And this is one structure, and the relation to the ring A is twofold. On the one hand, we have a multiplicative map from A to the rational bit vectors of A, which sends A to the polynomial 1 minus AT. And this is actually a multiplicative map. It's not additive, huh? It's not additive, this map. Okay, these are things we need to know about the rational bit vectors. So now we want to construct our functor, and the first thing is, if we start with the scheme, we have to change the structure sheaf. So for a scheme X, so for example, you can think of the spectrum of a ring R0 as above, finitely generated ring R0 over Z. We get a pre-sheaf, Zariski pre-sheaf by the following definition. If you have an open subset, then we send it. So the sections of this new pre-sheaf, are just the rational bit vectors of the ordinary sections. So this gives us a pre-sheaf. It's not a sheaf, they don't glue. So what we do is we sheafify. This is the associated sheaf. I call it the rational bit vector sheaf. Okay? And then by a general property, the stalks of this associated sheaf are the same as the stalks as the rational bit vectors of the stalks. This is not difficult. And so now, if you're given a scheme, so this is a topological space with a structure sheaf O of a special type, we can make a new sheaf from this rational bit vector sheaf, and it has this property on stalks. And so we define a new ringed spaces now, topological space with a sheaf of functions, which we call W rat of X. So X was the scheme. As follows. So the underlying topological space is the same one as before, but the sheaf is a new one. So this is a ringed space. Okay. This is a ringed space. So we have changed the structure sheaf of our scheme, replacing it by this rational bit vectors sheaf. So next step is to say what is a morphism. I want to say what is a morphism from one rational bit space for the scheme Y to the rational bit space of the scheme X. And firstly, is a morphism of rings. Such a morphism is a morphism of ringed spaces. Clear. But even if you're dealing with schemes, you need an extra condition. I mean, the morphisms between schemes are not all the morphisms of ringed spaces, but only the morphisms of locally ringed spaces. There's a condition. Otherwise, you get too many morphisms. But our spaces are not locally ringed spaces, and we need some replacement. So it's a morphism of ringed spaces, F consisting of a map on the topological spaces and the sheaf map. This is just the usual thing, which is local in the following sense. And this is really the important condition that one has to find. For all points Y in Y, there exists a unique map which has somewhat complicated notation, such that the following diagram is commutative. So let's look at the rational bit vectors of OX in the point F of Y, which is the same as the stalk of the rational bit vector sheaf of OX in F of Y. Then by this map Fis, or the stalk of the map F Fis, we have a map which goes here. And so this is what, because it's a ringed space, a morphism of ringed spaces, we have these maps. Now here we have a projection to the rational bit vectors of the residue field in the point Fy. And here we have a similar projection to rational bit vectors in Y. And the condition is that there should be a map here which fills this diagram. And it is truly a condition, because if it exists, then it is unique, because the vertical map on the left is surjective. So these are rational bit spaces attached to schemes, and these are morphisms between rational bit spaces. So there are some examples. First, not very surprising, a morphism alpha from Y to X, an ordinary morphism of schemes, induces a morphism between the rational bit spaces. In a natural way. So if you sit down, you will find how to define it, and you can check the conditions. the new locality condition follows from the locality condition for morphisms of schemes. And it turns out this functor is faithful. It's faithful. However, it is not fully faithful. There are many more morphisms between the rational bit spaces than between the schemes. For example, on the rational bit spaces, we have Frobenius morphisms. So Frobenius endomorphisms F nu of the rational bit spaces of X for all nu greater or equal to 1. And how do you define them? Well, the underlying map on the topological space is the identity, and on the sheaf map is just is induced by the Frobeni on rational bit vectors. And since they are functorial by change of rings, such commutative diagrams exist automatically, because the maps are just, the horizontal maps will be the Frobeni. So these new spaces, they have Frobeni, contrary to the schemes themselves. Frobenius is very, very important and useful in characteristic P, but it doesn't exist in characteristic 0 for schemes. And this is a remedy. On the rational bit spaces, you have all the Frobeni that you want. Okay, so now we have the rational bit spaces. These are some new ringed spaces. And now I want to define what the complex points of such a rational bit space are. What are the complex points? Because eventually we want to have a topological dynamical system on something. And so we define this in greater generality than the complex points. We say what are the S-valued points where S is any scheme. So if X and S are now schemes, we want to say what a morphism F from S to the rational bit space of X, what this is. And now we go from a scheme, which is one type of ringed spaces, to the rational bit space, which is another type of ringed space. And we define it in the same spirit as before. So this is a morphism of ringed spaces F consisting of a map of the underlying topological spaces and a map F-is. So that's a morphism of ringed spaces. So these are certain conditions. And again, we need some locality, which is local in the following sense. Very similar as before. So now for all S in S, there exist, they are unique, unique Fs twiddle fis ring homomorphisms, such that the following diagram is commutative. Very similar as before. We take the rational bit vectors of the stalk in F on S. Then we go by Fs fis to OSS. Here again, we have the projection to the residue field. And here we have the projection to the residue field. And the condition is that this should be possible to complete this. Okay. So this is the definition of a morphism from a scheme to a rational bit scheme. And let's give an example. There are canonical ring homomorphisms from the rational bit vectors of A to the ring A, ring homomorphisms. And they go as follows. If you have a rational bit vector, which we can view as a rational function, we map f to the logarithmic derivative at 0. This is a ring homomorphism. Yeah, remember that addition on the rational bit vectors was multiplication, and multiplication by logarithmic derivative goes to addition, so it's additive, this map, and it's also, as one checks, multiplicative. So we have canonical maps in this direction, and they induce a canonical morphism in our sense from a scheme X, from any scheme X to the rational bit scheme of X, bit space of X. This is something that comes with every rational bit space. You always have a canonical morphism from the scheme to it in the sense above. And this gives an injective map from the S-valued points of X. These are the morphisms from S to X by definition. And they go to the S-valued points of the rational bit space. The S-valued points of a rational bit space, like for schemes, are defined as the morphisms, as we just defined them, from S to the rational bit space of X. A set of such morphisms. Huh? And how does it go? Well, if we have an S-valued point, which is a morphism from S to X, we simply compose with F. It turns out to be injective. So, in particular, this is important for us, the C-valued points of X, so these are the classical points, C-valued points, they go injectively to the rational bit, the C-valued points of the rational bit space. Now, what does it, as for schemes, one writes C-valued points, where in reality one means the S-valued points where S is the spectrum of C, and for other rings too. For example, if X is given by a system of Diophantine equations over Z, like in the beginning, some polynomials, then the complex points of the resulting affine scheme are just the complex solutions of the system of polynomial equations, which will be an analytic space. Yeah, but this will be much smaller than the complex points of a rational bit space. So, special case for this is the one we are particularly interested in. If we start with something like the spectrum of Z, yeah, which is kind of a super interesting object because it contains, well, it gives rise to the Riemann zeta function, all the number theory. In this case, unfortunately, the complex points are very, very few. Yeah, the complex points are there's just one complex point corresponding to the unique embedding of Z into C as a ring. And but the new points, so the complex points of the rational bit space of the spectrum of Z is very big. Yeah? It's in fact infinite dimensional. So maybe something interesting can be done on this complex space, the new complex space, which could not be done on X of C. X of C is just a point. One philosophy is that you want to study the Riemann zeta function, which is an analytic object, using some global analysis on manifolds or dynamical systems. But the ordinary complex points, they are just a point, you can do nothing. And so we try to define more interesting spaces attached to spec of Z, on which perhaps one can do more. And this is a step in the right direction, I think, but it is not eventually the final object. So then now I tell you, one can put a natural topology on the rational bit spaces, the complex points of the rational bit space of X, such that, for example, X of C with its analytic topology is a subspace. Well, we have this inclusion, and there's a topology which prolongs the one on the usual space, and which is functorial, and so on and so on. So, but I don't explain how to do it, but it is a very natural construction. So now, but I will explain how to construct dynamical systems. Construction of dynamical systems attached to a scheme. So first we do it for normal schemes. As I said, normal, if the scheme is the spectrum of a ring, then normal means that it's an integral domain which is integrally closed in the quotient field. So that's something which can be achieved by normalization. You can assume it. So for normal scheme, x0 over z of finite type over spec z. Consider the following abbreviation: x0 dot of c. The dot signifies these are new complex points. So this is an abbreviation for the complex points of the rational bit space of x0. Okay. This is just an abbreviation emphasizing the role of new points. So this has action by the Frobeni. The rational bit spaces have an action by Frobeni, and it induces one on the complex points. And it turns out in this situation that the Frobenius morphisms are injective. Now we have infinitely many commuting endomorphisms. You can also say that for the prime numbers, for each prime number, we have an Frobenius FP and they commute and so on. And we want to organize all these Frobeni into one action by the real numbers. We want to make a suspension construction. And for this, it's necessary to invert the F news, so we get not only a semigroup, but a group which acts. So second step is we have to invert the guys, invert the F news. Oops. And this can be done in a formal manner by passing to a union or co-limit. So co-limit over the F news x0 dot c, which inverts them. So it's the same process if we have the natural numbers, we have the multiplication by natural numbers. So sorry, we have the integers and we have the multiplication maps by natural numbers, and these multiplication maps are injective, and we want to invert them, and then we pass from the integers to the rational numbers, and somehow this is similar. So you can write down the points of this co-limit. You can write as expressions like this, where p is an x0 dot, and you say that two of them are equal. If and only if f mu of p is f nu of q. And here p and q are in previous points. Yeah? And so this is something simple. By the way, it's a co-limit on spaces. And so if you look at functions, it will be a limit on functions. And this process is very similar to tilting, to passing from to something which is not perfectoid to something which is perfectoid. Okay, so now the F-news become homeomorphisms. And they organize into a group. We can generate a group, namely the group of positive rational numbers under multiplication. And we get an action of this group on our space now. And we want to next, we want to turn this into an action by the reals. And this we do in a standard fashion, namely we form the suspension. So this will be the space of our dynamical system, the underlying space. We take the product of these rational bit spaces, where now on which the Frobenia have been inverted, or their complex points. We take the product with the real number, positive real numbers, and we divide out diagonally by the action of the positive irrational numbers, so diagonal action. Positive rationals are a subgroup of the positive reals, and we have just seen that via the inverted Frobenia, they act on x0 hat, and so we get this space, and this space now has an action by the positive rational numbers. So it has an action via, so V acts on an orbit under this Q action just by multiplication in the second component. Yeah. And of course we can exponentiate to get an R action. Yeah, completely trivial, of course, but these are more standard, these additive actions. So we multiply with e to the t in the second component. Then we get an R action. Okay, then we have some theorems. Now we have our dynamical system. Huh? So first result is that this is connected. I mean, to construct a disconnected dynamical system with the right periodic orbits for an arithmetic scheme, this is easy, yeah? But it has to be in a suitable, a reasonable topological space, and of course it has to be connected, otherwise it's useless. This thing is connected, but the structure is complicated. It's not path connected. In fact, it has uncountably many path-connected components. So the x0 has a structure which is not as complicated as this an attractor, but it goes in this direction. Yeah? So x0 is far from being a manifold. So the proof is not easy. The proof uses resolution of singularities in characteristic P, which has not been proved, but we need something weaker. We need de Jong alteration theory. At least if our x0 is higher dimensional. For dimensions 1 and 2, one can use easier results. And we also need some arithmetic on the adels. To prove this. So it is not an easy result. Theorem 2. The fact that it's connected should be related to the, well, now let me say nothing about this. Theorem, so that's theorem 2. And now the result, which makes the connection to the things we said in the beginning. Let's look at the points which are on which there is isotropy. So talk in terms of the action of the positive reals, multiplicative group of positive reals. So those points for which the isotropy group is non-trivial, yeah, which lie on a closed orbit, this set is equal to the following. It's parameterized by the closed points. So this is the set of closed points, which in the case of rings corresponds to the maximal ideals. Spectra of rings corresponds to maximal ideals. And if x0 is the spectrum of Z, then the closed points correspond to the prime numbers. So gamma x0, closed points, so they correspond to the maximal ideals. This is the isotropy group. So they have something, so these periodic points have something to do with or the points lying on periodic orbits have something to do with the closed points. But the correspondence is not one-to-one, but they come in packets. Huh? So wherefore x0 in gamma x0, we have that the isotropy group is the cyclic group generated by the norm of x0, the corresponding closed point of the scheme. This will give us additively the right length. And what is the structure of the gamma x0? Moreover, gamma x0 is a fiber space, compact fiber space. It's a compact fiber space over the following compact group: automorphisms of the finite field Fp bar as a group divided by automorphisms of the finite field Fp bar as a field. So in some standard notation, this is, well, for the experts. We can write it like this. So it's a compact group, yeah? And whose fibers are the closed orbits of length log of norm x0 if we talk about the action by the additive group. In fact, this fiber space is almost a product. Yeah. So before I explain a little more what the result means, yeah, my time is practically up. Let's say one word about the proof. So the proof, one reduce to the existence of Frobenius elements in Galois groups. That's the slogan, eh? But a lot of work is necessary to do that. But the existence of Frobenius elements for prime ideals, this is something really, really basic. And this is the best reason. This is the reason, and it is really the best reason morally for periodic orbits to arise. So the moral is therefore thus the closed points x0, oops, of our scheme, yeah, they correspond bijectively to the compact packets gamma x0 of periodic orbits in x0 phi t. Every periodic orbit lies in a unique gamma x0. So in particular, our dynamical system knows the Hasse-Weil zeta function. I have not been able to define fuller indices in our situation because these gammas they have a p-adic or a totally disconnected direction and an Euclidean direction. But it should be possible to attach fuller indices to such packets and then define a generalized Rayleigh zeta function, which would then turn out to be the Hasse-Weil zeta function. So these are two main results. Another result is I've been trying to find a smaller dynamical system than this one by looking at the periodic orbits and looking at the topological closure of the union of the periodic orbits. And I've been able to determine this, granting some in higher dimensions. I had to assume some as yet unproven things, which one probably can prove. So I've determined the topological closure, but it's still infinite dimensional. What I would like is something finite dimensional, but there will be some modifications necessary. Also, there is a very close relation between this construction, which I gave to you, and the construction of Peter Scholze and Robert Kucharczyk, who attached Galois groups to, who interpreted Galois groups of certain fields as fundamental groups on some exotic topological spaces. They have no dynamics, and this is the zero-dimensional case of my construction, it turns out. Okay, thank you very much.
Thank you very much for beautiful talk. Are there any questions or comments?
Yeah, so I thank you for your talk. I'd like to have some questions. So first, can you go back to where you define the Frobenius F new, and then you say that is injective. Somewhere here. No.
So these are the Frobeni on the rational bit space, yes?
I mean, you say that the Frobenius is an injective map. Yeah, here. Right.
Where do I say it? Injective, yes. Mm-hmm.
Yeah. So if you are injective, so why don't you just take the intersection of all the orbit of this, and so you will get a subspace which is, I think, is the smallest space that is invariant by this by the orbit of this F new. So I mean, you take, for example, you take
I understand. What you are doing is you are taking the projective limit, over the F news.
Yeah. And
that does not work.
Does not work.
It was the first thing I tried, yeah. Mm-hmm. Yeah.
What does not work? What I mean, what
does not work?
Yeah.
Well, the truth is that I did not mention some complications in the construction. The connectedness result is true in general, but for the result on the periodic orbits, you need to add some technical conditions on the space, on the points of the complex space. Yeah, I forgot to mention this because it's a little difficult to explain. And if you do that, then this intersection becomes empty. But it is necessary for the orbits.
Okay. Then the second question. So you just find a space. So you take the co-limit. So I guess it's not compact, right?
Oh, it's not at all compact, no.
So do you have some natural compactification that then you can extend this your map to?
Well, in arithmetic geometry, it's something like the spectrum of the integers for a number theorist is not a compact object, because what is missing is the Archimedean place, the Archimedean valuation. The spectrum of Z, the closed points, the prime numbers, they correspond to the non-Archimedean valuations. You need the Archimedean valuation. For example, then you have the so-called product formula in algebraic number theory. So in algebraic number theory, you always need to complete by the Archimedean places. Or if you look at the functional equation of the Riemann zeta function, if you want a functional equation, you have to add another factor, Euler factor, the one for the Archimedean place, and this is the Euler gamma function, yeah, this gamma factor, which you need to add to get a good functional equation. This also reflects the fact that spec of Z is not compact. So my construction, what I do here is I take this open thing, this non-compact x0, or for arithmetic purposes, all these guys are non-compact. And what is missing is to do something for the at infinity, yeah, for the Archimedean places. And I don't know how to do this, but this is something that one has to understand, and that should lead to a natural compactification.
Okay.
That is an important open problem. And you are right, compactness in some way is required. To prove something.
And you also missing commutative theory, right?
Sorry, which kind of theory?
Yeah, you're also missing some commutative groups, right?
Yes, I mean the connectedness is the H0 with constant coefficients. I've also looked at a kind of leafwise cohomology. You take the sheaf of functions which are locally constant on this x0 dot direction, yeah, but which can be continuous in the dimension of the positive real numbers in this component. So that's a bigger sheaf than the constant sheaf, and it is still true that its global sections are just the constants. This is even harder than to prove connectedness. So that is the H0 sheaf of this leaf of the H0 cohomology of this sheaf which is inspired from foliation theory. And the hope is that the H1 of the same sheaf will have to do something with the non-trivial zeros of the Hasse-Weil zeta function. But even the H0 is difficult, and the H1 I have not yet been able to calculate. But the hope is these dynamical systems have a kind of one co-dimensional foliation. I mean, you see these x0 hat C, yeah? The images of their, yeah, you have a kind of foliation. I mean, it's not locally trivial, but you have a partition. And the transversal direction is the direction of the flow. So that will be one codimensional. And now you are in foliation theory. If you have a foliation, you can look at the sheaf of functions which are locally constant on the leaves. Continuous everywhere, but locally constant on the leaves. And these are the sheaves that I think, or the cohomology of these sheaves are the ones which should know about the zeros and poles of the zeta functions. And I think this because of because if the spaces are nicer, manifolds, foliated manifolds, one codimensional foliated manifolds, then one has such relations now for the real zeta function instead of. So their zeros and poles can be expressed in terms of the spectrum of the action on these leafwise cohomologies. And the hope is one day to explain the zeros and poles of the Hasselbalch zeta functions in a similar way on more complicated spaces. This would allow some pretty dramatic consequences.
Okay,
but it's still a very far way off.
Yeah, and did you put this on like archive or some?
Yes, it's
okay.
on the archive.
Okay.
I also explain how. I also look at p-adic points, not complex points, but p-adic points. And in my dynamical system, I then find a very natural subdynamical system, and I calculated this, and it turned out in a very, very simple case to correspond to be a natural bijection to the points of the Fontaine-Farr curve from p-adic Hodge theory, which is a very, very good object. And so we get from a global approach in a non-trivial way, we get to this interesting objects in p-adic analysis.
Yeah. Okay. Thank you. Yeah.
So the title is Dynamical Systems on Arithmetic Schemes. It's on the archive.
Are there any other questions or comments?
Yeah, I have a question. So in your construction, you have three steps. So for instance, if you stop at the step 1, you already have a kind of a discrete dynamical system. Is that right?
Yes.
And then what can you do just using this discrete dynamic system? So why do you have to go to this R positive real number action? For example, if you have a discrete dynamic system, you also have the so-called arithmetic dynamical zeta function.
Well, but these are arithmetic, I think, is for one automorphism, but here we have many commuting ones. Of course, you can say what the closed points are in terms of the many commuting ones, but I mean, if you want, in analytic number theory, there are formulas which relate the zeros of zeta functions with the prime numbers or the closed points. And these are the so-called explicit formulas in number theory. And they were invented by Riemann in his original paper. There's the first of these formulas, and later they were taken up by André Weil in the 40s, now I'm not sure, 50s, maybe 1950s, who gave them a different interpretation. And he interpreted these explicit formulas as an equality of two distributions in the sense of Schwarz distributions, an equality of two distributions on the real line. One coming from the zeros, non-trivial zeros and poles of the Riemann zeta function, and the other one coming from the prime numbers and also the Archimedean place. And similar formulas, really very, very similar formulas, arise in the theory of one codimensionally foliated dynamical systems as a transversal index theorem. Yeah, there you have the real numbers acting, that's the Lie group. And you have the elliptic operator for the foliation elliptic operator, this complex. And it's elliptic only in the leaf direction, but at least the group action is transversal to the leaf direction. So you have this kind of control, which this combination, which is studied in a field which is called transversal index theory. There's a book by Attia, a lecture note for, in the case where the group is compact, but here the group is non-compact. It's the real numbers. Anyhow, there's a result. The only result from non-compact groups of a transversal index theorem was proved by Alvarez, Lopez, and Kordyukov, and they showed a transversal index theorem. Yeah? And this transversal index theorem is stunningly similar in structure. It's, again, an equality of two distributions on the real line. It's extremely similar to the explicit formulas in number theory, again, by substituting periodic orbits and their lengths by the prime numbers and their logs, and so on. And so I think, so therefore I've always been looking for a continuous time dynamical system in order to then prove such a transversal index theorem. And in this, well, in this way make the relation to the zeta function. The transversal index theorem plays the role of the Lefschetz trace formula which for a single endomorphism. But if you have many commuting ones, you suspend them, you get a continuous time thing, and then you get this equality of distributions. It's a more general thing. Sorry. Mm-hmm.
Thank you. Thank you.
Are there any other questions or comments? If no, then thank you very much again for speakers.
Thank you very much.
Okay, so welcome to the afternoon and final session of the conference. The first speaker is Charles Favre, and he's going to talk about topological entropy of rational maps. Yeah, so please.
Okay, so thank you very much. Thanks to the organizer for giving me the opportunity to talk at this conference of my joint project with the Junichi and Centro. So the talk is going to be, let's say, the crossroad between dynamical system and algebraic geometry. And my aim is to explain how we can bound the topological entropy of endomorphism. So in my original title for rational map, but here I'm going to focus on endomorphism of the projective space of dimension L over K, and K will be any field. Okay, so let me start by recalling what the topological entropy is. So my handwriting is not super good, and on the tablet it's even worse. So do not hesitate to stop me if anything is unclear. So the topological entropy is arguably the most fundamental invariant of a dynamical system. And it was introduced in 1965 by Adler, Konheim, and McAndrew. And here is how it goes. So, so you start with the continuous map, self-map, F from X to X. So X is your favorite compact space. So compact here is important. And F is continuous. And what we're going to do is we're going to attach to, so we're interested in looking at the dynamical system induced by this self-map. So we're going to look at F to the M, which is defined inductively by the following formula, where F0 is the identity. So F to the N, the composite map F composed with F n times. And so we're going to attach to such a self-map, such a dynamical system, a number that we call H top, or that we denote by H top of F, which is a topological entropy, and which will be non-negative real number, which is possibly plus infinity. And what is this number? Well, it's a rough, so it's an invariant that measures somehow the dynamical complexity of your system. Okay, so let me explain how Adler, Konheim, and McAndrew define this number. So you start with open affine cover. So let me call calligraphic Q. Is any open cover. And since your space X is supposed to be compact, you know that you can always extract a subcover which is finite. And let me define the complexity of an open cover. Let me denote by n of u to be, well, the cardinality of a minimal subset J inside I such that the union of all ui in J cover X. Okay, so the complexity of an open cover, it's just an integer. And this is a number of pieces from your open cover that you need to cover completely your space X. Okay, so, well, so now you have an open cover. You let the dynamical system act on this. So what you can define is a sequence of open cover by this joint operation. So inductively, so U1 is equal to U, then U2 is the joint of U with the preimage of U1, etc. And so in practice, what is the piece inside? So if you have an element in UN, this is something of the following form. So it's UI1. So this guy is in the original open cover, intersected with F minus 1, maybe I should say UI0. Preimage of UI1, etc., intersected Fn minus 1, UIn minus 1. Okay. So this is an open cover, and one can check. So well, this is a sequence of open cover of X, and one can check the simple facts that the complexity of the sequence of open cover is submultiplicative. So in other words, the complexity of the open cover index n plus m is less or equal to the product of the complexity of un times the complexity of um. And so you have this wonderful Fichte's lemma that says that under that conditions, well, you can define the limit as n tends to infinity, 1 over n log of the complexity of un. So this guy is well defined, is equal to the infimum, in fact, of this sequence. And this is a number a priori, which is, well, non-negative plus. So in that way, you get a number that depends, well, that measure the growth of the complexity of your open cover pulled back by the dynamics. So it depends, obviously, on the choice of U. And since you want something that does not depend on the choice of any open cover, you better take the supremum over all open cover U. Okay, so this is a definition of the topological entropy. So it has some the following property that it distinguishes some. So okay, sorry, it's invariant under conjugacy. So if you conjugate your map by some homomorphism, you get exactly the same number. Okay, so I'm not going to. Okay, so let me say right away what is my goal today. Well, it's estimate the topological entropy for a class of algebraic maps. So for maps F, which is an endomorphism. Oh, yeah. Okay, sorry. I have a problem with my tablet, of course. So just 1 second. Okay, let's see if it works. Yeah. Okay, so my point is to try to estimate the topological entropy for a class of algebraic maps that are endomorphism of the projective space of dimension L. Okay, and here it's defined over some field K. And so at the beginning, I'm going to discuss the situation where the field K is, let's say, the field of complex numbers, and then we're going to turn to the case where K is a complete metrized field, but which is a non-Archimedean. Okay, so just to recall exactly how this such a map is given in homogeneous coordinates by L plus 1 polynomials. So P0 of Z, etc. P of Z. So the PIs are homogeneous polynomials in Z of some degree, let's say D. And the fact that F is an endomorphism, so here I draw an arrow. So to be an endomorphism is equivalent to assume that they do not have, all these PIs do not have any common zeros. Well, maybe except the point 0. Okay, so so let me start by a warm-up. And so K is arbitrary here. So PL of K is an algebraic variety. So I'm going to endow this space with the Zariski topology. Okay, so you can topology. So you can always argue that this topology is not a Hausdorff. So it's not a compact space, but it's also possible to make, I mean, if you look at the definition of the topological entropy, we didn't really use the fact that the space were Hausdorff. So you can define the topological entropy also of any continuous map from P over K to itself, and over the Zariski topology. So what is the theorem here? So the theorem is that so for any endomorphism, the topological entropy of F on, so let me call it ZAR here, just to emphasize that I'm endowing PL with the Zariski topology, then this is equal to 0. Okay, so it's not super surprising, it's not very surprising, because in some sense, so let's say when L is equal to 1, what can you say about the dynamics of a map on a curve? Well, points, they have two choices. Either their orbit is Zariski dense. So Fn of a point is Zariski dense. Or it's finite, meaning that X is then preperiodic. Okay, so the dynamical system from the point of view of the Zariski topology is very crude. So in other words, Zariski topology, you don't have, in Zariski topology, you don't have that much open sets, so it's very hard to distinguish points. And so the dynamics is not very interesting. So the fact that the topological entropy here is 0 is somehow reflects that, that property. So I'm not saying that it's not interesting to study problems on with this Zariski topology. So there are a lot of conjecture in arithmetic dynamics, where you look at map from algebraic space to itself and go with the Zariski topology. Okay, so let me give an indication of the proof, at least in the case where L is equal to 1. It's kind of elementary in that case. So in higher dimensions, it's a bit more complicated. There's some kind of induction that I don't want to explain here. So how do you prove that topological entropy is 0, let's say, for map F from P1 to itself? Okay, so you start with your favorite open cover. And so now in dimension 1, so you have this nice fact that Zariski open set is just a complement of a finite set. So UI for each I is P1 minus some finite set. Okay, so let's take, let's say, U0. It's P1 minus F0, F0. So let me assume that this is non-empty. So F0 is finite. And now we're going to estimate the complexity of UN by induction. So remember, UN is this U, the joint with the preimages. So pullbacks, if you want, by the dynamics of this open cover. And so let me suppose that V1, Vm are pieces or elements inside UN that covers, so covering P1 of K. So that M, this M is the complexity of UN. And now you want to build a new covering of UN plus 1 out of this that cover P1. Okay, so what you can do is that you look at U0 intersected with S minus 1 of V1, etc. U0 intersected with F minus 1 of Vm. So what do they do? Well, this is a family, a finite family of open sets. The cardinality is equal to M, and it covers almost everything. So what it covers U0. So it covers, well, P1 minus F0, and F0 is finite. So using this, what you show, well, what we have shown here is that the complexity of UN plus 1 is in fact bounded from above by the complexity of UN, or maybe here it's not M, it's N, sorry. So this was my index M, plus the cardinality of F0. And so this implies that the growth of the complexity of UN is linear. Okay. And so having a linear growth implies that the topological entropy, which is 1 over the log of this, is 0. So you could expect that in higher dimension, the growth of any, the complexity of this UN is also polynomial. So we don't quite prove this, but still we're able to show that that theorem that topological entropy for Zariski topology is equal to 0. Okay, so so what it says that we need to put some to use some finite topology on this productive space, and to do that we need to metrize the field K, and so I'm going to work with complete metrized fields. So I'm going to endo K with norm. So a norm is a function from K to R plus. And once again, I have problem with the battery. So that satisfies the standard inequality. So it's a standard axiom, sorry. So the norm of X is 0 if and only if X is 0. It has to be multiplicative. So the norm of X times Y is its product of the norm of X and norm of Y. And we have this triangular inequality. Okay, and so there is basically two categories of such fields: Archimedean ones and non-Archimedean ones. So the Archimedean ones, you don't have that that many options. Basically, you have R and C with the standard norm, and but on the other side, you have many of them. So you can think of p-adic fields, infinite extensions, or not actually. So QP, CP, etc. You could think also at the field of formal Lorentz series. So here over any field. So here I'm going to discuss a little bit more the case where the coefficients are complex numbers. So what is this? This is a set of series. So let's say AI T to the I. So the AI are complex. And here it's a formal Lorentz series. So meaning that for almost all negative coefficients, AI is equal to 0. So in other words, there exists some n integers such that the sum starts only from integer larger equal to n. And here, so what is the t-adic norm here? The sum of AI ti is the exponential minus the minimum of all index I such that AI is non-zero. Okay, so the norm measures, if you want, the order of the pole of your formal Laurent series. Okay, so one point here is that, so okay, maybe I should have said this at some point. So what is the non-Archimedean? So in a non-Archimedean case, in fact, this inequality here, triangle inequality, sorry, becomes the strong triangle inequality. So the norm of x plus y is less or equal to the max of norm of x, norm of y. And so the analysis somehow becomes more simple. And then the, yeah, okay, let me put this one. Okay. So the situation, so let me come back to my original problem to computing the topological entropy of an endomorphism of the projective space. So over the field of complex numbers, this is something that is well known, let's say, since the end of the early 90s, late 80s. And so our project with Juni and Thuyen was to extend some of the result that we know over the complex to the non-Archimedean case. Okay, so it's not completely clear why we should do some non-Archimedean dynamics. So let me just say one word about well, possible applications. Not exactly of what we did, but of non-Archimedean dynamics. As application or motivation for doing non-Archimedean dynamics, I don't know. So NA for me is non-Archimedean. So basically you have two kind of, you have two set of applications. So in mixed characteristic. Okay, my handwriting is really poor and poorer. So characteristics. So it means that you work over a p-adic field. So then you have a lot of application in arithmetic dynamics. So I think that the last talk today is by Oguiso. And it exploits, I mean, I don't know what is going to talk about, but it exploits somehow some dynamics. It relies on some, still some dynamics over a p-adic field. So in arithmetic dynamics, you can try to get some height bounds for iterates of points of a dynamical system, let's say, that is defined over a number field. And then let me put this very roughly. If you're a number field, then you can try to apply some local global arguments. And so you're naturally interested in looking at the dynamics at each finite places. And so, well, so that one motivation to understand the dynamics of our p-adic field. Then there are some other motivation comes from the so-called p-adic method. Let's say p-adic parametrization, lemma, theorem, method. And that gave very strong application. So there is a very famous, very strong papers by Quinta and Juni that apply this p-adic parametrization method to understand the group of birational transformation or automorphism of algebraic variables. Okay. Yeah, well, okay. So there are many people that I should cite here, maybe Silverman, Kawaguchi, etc. I'm not going to talk about this. So I'm going to be very quick. There is a second, so this is, let's say, a first set of application to the study of dynamics over non-Archimedean field. Second set is in equicharacteristic on equal characteristic zero. So basically here, what you assume is that you assume K to be the field of complex formal Laurent series with the t-adic norm. Okay. Let me check again. Sorry, I have a problem with my tablet. Apparently there's okay, so unequal characteristic 0. So what is the idea here? So the idea is that studying the dynamics of endomorphism of that field gives you information on degeneration of a holomorphic dynamical system. So let me explain right away why there is a connection between holomorphic dynamical system and dynamics over this. So there are many people here that I should cite. So Jan Kiwi, Pilgrim, Nye, Luo, DeMarco, Faber. So a lot of papers that exploit this connection here. So what is the connection? So you start with not just a single endomorphism of PL over C to itself, okay, but a family of them. And you take this family to be, let's say, parametrized by the holomorphic, the unit disk inside the complex plane. And you assume that this family is holomorphic in T over the punctured disk and meromorphic at T is equal to 0. Okay, so on D. So in other words, this FT, if you look at this in a homogeneous coordinate, they are given again by L+1 homogeneous polynomials as before, except that these polynomials now, they don't have complex coefficients. So they're homogeneous polynomials in Z, but the coefficients are holomorphic function on the unit disk. Okay, so it's a ring, and you can view this ring as a subring of the field of formal Laurent series. And so this family of holomorphic function, it defines naturally, let's say, a map, algebraic map, capital F from PL over this field of Laurent series to itself. And so all these people that I mentioned, Kiwi, Favre, Pilgrim, etc., and so on and so forth, they exploited this thing here, that saying that some properties of the holomorphic dynamical system of the holomorphic family has some consequences on the dynamics of capital F and vice versa. Okay, so it's going to come back later on during this talk when I'm going to estimate the topological entropy of endomorphism over that field. Okay, so let me discuss now the Archimedean situation before I state our main theorem. So I'm not sure if everything is okay. If you have any questions, and you have to you stop me, right? The Archimedean case. So the Archimedean case is when the field K is equal to the field of complex numbers.
Sorry, Charles.
Yeah.
I'm Cinzia. Could you give a reference? Could you write a reference for what you were saying just before about OD, the link among the end of exactly? Can you write because it was not clear from?
Okay, so I mean, if you have a holomorphic function, it's you can think. I mean, you can expand it into a formal power series, and so it's even stronger than this. It's not only inside this, but it's also a formal power series. And this guy is inside the formal Laurent series is a field of fraction of this guy. Okay. So what I'm saying here is that this FT, you just interpret the coefficient of your polynomials as element in this new field. And so this defines naturally an endomorphism over this field.
Okay, but you have mentioned people. Can you write the person who are working on this?
Okay. Let me do this.
Thanks.
I have to do this here. Okay, so let's say here we bring. No, so I'm not citing everyone, and so if somebody in the room feel uncomfortable with the set of people that I mentioning here, just raise your hand. Marco, Faber, and many others. Okay. I mean, I cannot write down the exact references, but if you're interested, you can just send me a message. I will be happy to direct you to the proper references. Okay. Okay, so let me come back to the Archimedean case. So it's a test case if you want, and this is so I'm going to state a theorem, which is due to, well, okay, Gromov. In fact, many people at the same times, but the proof I'm going to explain is really due to Gromov. And here I have to cite many other people. So, okay, Yamdin, Mizurevich-Pertitsky, etc. Okay, but so here the proof is it's a proof by Gromov. So okay, so what is the statement? So you take your favorite endomorphism from PL over C to itself, and assume it has degree D. So remember, what is a degree? This is a degree of the common polynomials that define F in a homogeneous coordinates. Then the topological entropy of that guy. Now with what, where you view PL of C as a complex manifold. So let's say on the analytification of PL over C. And what is the formula? Well, now it's non-zero. It's equal to L times log of D. Okay, so for instance, if L is equal to 1, if you have an endomorphism of the Riemann sphere of degree D, well, its topological entropy is equal to log D. And if you increase the dimension, you have to multiply by the dimension. Okay, so in fact, this statement, this equality here is actually two inequalities. So we have the lower bound and the upper bound. And what Gromov did was to give a very neat, very nice proof of the upper bound. So I'm not going to say anything on the lower bound. It's a consequence of a very strong theorem by Yamdin, or a very simple inequality proved by Mizurevich-Pertitsky in a much greater generality. Okay, so here, ... And we're going to see that in the non-Archimedean case, this lower bound is, you cannot use any of these arguments by Yamdin, etc. in the non-Archimedean case. Okay. Upper bounds. So this is a proof by Gromov, and I'm going to explain it. Okay, so what is the idea? The idea is to relate this topological entropy to the growth. So we know that this is connected to the growth of the complexity of, let's say, pullback of upon covers. And here what we're going to do is we're going to relate this to the growth of volumes of complex, or let's say of the graph of Fn, of the iterates. Okay, so how do you compute the volume, of a complex submanifold in, let's say, projective space? So, well, you better fix a Keller form. Let's say on PL, so the Fubini study form. And if Z is an, let's say, analytic or algebraic subset well, its volume with respect to omega is just the integral. So let's say that z as dimension L prime is irreducible, and its volume is the integral over z of omega to the power L prime. Okay. Okay, so what is the idea of Gromov? Well, the idea is, so exactly as said here, is to relate these things through the growth of volume of the graph of Fn. So we're not going to look exactly at the graph of Fn, but some kind of twisted way of this graph. So we're going to look at, so n is any integer. So we're going to look at gamma n, which is going to be the set of n tuples. So x, f of x, blah, 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 fn minus 1 of x. And so this is inside PL of c to the power n. Okay, so some kind of graph, right? So what is the graph? Well, the graph would be to take only x and the last one. Well, okay, so that would be the graph of fn minus 1. But then it would sit in PL to the power n minus, well, to PL to the square. Okay, so here we collect all the information of the whole orbit from, let's say, time 0 to time n minus 1. Okay, and so I'll have to explain why this topological entropy is connected to the growth of the volume of gamma n and how to estimate the volume of gamma. Okay, so there's two parts somehow. Okay, so well, so we start with some open cover. So we work over PL or some manifold. Omega is defines a metric. So we look at the so what is natural to do is to look at the open cover given by balls, omega balls of diameter epsilon. And then, so it depends on epsilon. We're going to see that the upper bound is always the same. Let epsilon tend to 0, and then we get the bound, the upper bound on the topological entropy. Okay, so let me just draw. So this is in PL to the n over C. So this is supposedly gamma n. And so the first observation is that the complexity of un, so un being the set of balls of diameter less than epsilon, is in fact bounded from above. Okay, well, in fact, it's equal, sorry. It's the maximal number of balls in this space here, in PL of C to the n, of diameter epsilon, centered at a point on gamma n, and disjoint. Okay, so you have a good geometric interpretation of this n of un. So this is a maximal number of ball of radius epsilon centered at a point in gamma n that you can pack and that are all disjoint. Okay, so now what is the game? The game is that you compute the volume of gamma n, and well, the volume of gamma n is less or equal to the volume of is greater or equal to the volume of the intersection of each of these balls with gamma n. Sorry, it's very equal to the sum of the volume of this ball of radius epsilon with gamma. Okay, and what we know is that there are n of un such balls, and so then there is the theorem. So it's complex analysis. So the theorem by Lelon that says that these volumes are always bounded from below by a universal constant. So it's in fact, so let's say some universal constant times this epsilon. So epsilon here is the radius of your ball. And so what you get is that the volume of gamma n is very equal to n of un times this constant times epsilon 2 to the L. Okay. So again, so what you want to do is estimate from above the log growth of this guy. And so this inequality here says that you only need to understand the growth of this volume. And then, in fact, this is a clever computation, cohomological computation. Of Gromov. And here I cheated from the very beginning, is that I didn't tell you with respect to which scalar form we are computing the volume of gamma n. So remember that gamma n is inside the product PL with itself. So what we do here is we look, so we have a scalar form on PL. And then you can pull it back by any of its the projection on each factors, and so we compute the volume of gamma n with respect to capital omega, which is the pullback by each of the projection of your original scalar form on omega. And well, so the computation is not particularly difficult, but it's purely cohomological. And then your Gromov was able to show that this thing here grows not less than well, the log, so 1 over n log of the volume with respect to omega of gamma n is less than some constant. Let's say what I say is L log D plus epsilon 1. So L log D plus eta to the n. And this is for any eta positive. So if you put this all together, you get exactly the upper bound that I stated here at the very beginning. Well, this bound, the upper bound for the topological entropy. Okay, so I should have, I don't know, how long does it last? It's like 50 minutes or 1 hour?
It's 1 hour or
okay, so
50 minutes maybe. 50 minutes plus questions.
Okay, so I have 10 minutes. So let me state a couple of terms, okay? So now the non-Archimedean situation. So what is a theorem? So the theorem is as follows. So K is a non-Archimedean complete metrized field. F is any endomorphism from PL to itself defined over K of degree D. Okay, then if you look at the topological entropy of F on the analytification of PL over K, then again, this is bounded from above by L times lot. Okay, so this is exactly the same statement as Gromov bound. So except that here I have perhaps to explain a little bit what these things means. Okay, so it's not, so when K is equal to C, this is the complex manifold PL defined over C, but when K is arbitrary and non-Archimedean, this is here. It is in fact the Berkovich analytification. Okay, so just before I continue, explain a little bit what this Berkovich analytification is. So let me say that, so this, we proved it long time ago with Rivera Letelier. in dimension 1. And so we have now a proof in all dimension with Chuyen and Jun. Okay. Okay, so I don't have much time to explain everything here. So let me try to convey at least some ideas about this Berkovich identification. So what I'm going to do is to give you just a couple of idea on how to generalize this Gromov argument to a situation, the non-argument case. And so I'm going to simplify a little bit the discussion. I'm going to assume that K is equicharacteristic 0. In fact, I'm going to assume that K is this field of Lorentz series with complex coefficients. So why am I doing this? It's not necessary. Okay, so the statement is true over any field. But here I can exploit more directly connection between complex geometry and the geometry over this field. Okay, so what is PLN over K? I'm not going to define this. It will take me more than 6 minutes. But let's say that this is something which is compact. So I'm insist on that point. It's not only quasi-compact, but it's compact and Hausdorff. It is locally connected. It's connected. Okay, fine. Doesn't say much. If L is equal to 1, it looks like a tree. So the Berkovich identification over any field is a tree. Not really defining what is a tree, but a tree is something which is one-dimensional and in which you cannot see any loop. So in other words, if you take 2 points, there is a unique path that join them. Okay, so the picture is something like this. I'm always drawing the same picture. The only thing is that you have to understand that this tree is very hairy. Not like me. So what does it mean? It means that the set, so here you see that you have some cross point here. You have 2 segments that cross some point. So this is a bifurcation point, or sorry. Yeah, well, I have I just cannot remind what is the right terminology anyway. So branch point, yeah, well, branch point, sorry. So you have to understand, so what I mean by hairy here, you have to understand that branch points are in fact dense in any segment, okay? And plus the set of branching at one point is, so here you see that when you see such a picture, the set of branches, it's at that point, you have 4 directions. So you have 4 branches. In this tree, in fact, the set of branches is uncountable. You have a canonical bijection with the projective space over C. So it's very hairy, but never mind. It's still compact, still locally connected, etc., and so on and so forth. Okay, and well, so if L is at least 2, situation is a bit more complicated. Then you're patching not only segments, but simplicial of dimension L. Simplices, sorry, of dimension L, but then the total space is homotopically trivial. Okay, so let me check. So I have 4 minutes. So I'm going to be a little bit quick, but I would like still to, so I have two options. Either I'm just stating one more theorem. I'll try to explain a little bit how we proceed. So let me choose the later option. I'm not going to get over more than 5 minutes. Okay, so to understand this, the structure of the Borkovich identification of PL over the field of Euro series, it's kind of quite a little bit involved. But so let me write this way. It can be understood in terms of complex geometry, in terms of the notion of models. So what I mean here by a model is something like this. So a model, by definition, this is a proper birational or bimeromorphic map. So let me call it birational proper over PL over C cross the unit disk. Okay, so here I'm really thinking about a complex manifold now. So PL, it's over C. So as a complex manifold, D is the unit disk as before. Okay, and so you have here the projection onto the disk, and here you have the projection pi. Okay, so when you have a model, let me assume that so here you can look at the central fiber x0, which is pi x minus 1 of 0. Okay, sorry, but I didn't say one thing. So the birational proper map here has to be an isomorphism. So this is something important. So mu is an isomorphism over the Punchak disk, so over PL cross D star. So somehow, so what is mu? Mu is in fact a sequence of blow-up on the central fiber, so PL cross 0, okay, and a finite sequence of blow-ups. Okay, so I'm going to focus on simple normal crossing models in that sense. So assuming that X0 has simple normal crossing singularities. And when you have such a thing, then you can define its dual complex or simplex, which encodes how the irreducible components of X0 intersect. So this dual complex, let me denote it by delta of X. And what is one way to understand the Borkovich identification of PL is through this dual complex. So first you can show that this guy is a subset, canonical subset of the Borkovich identification over the field of Euro series. And in fact, so when X is so X is obtained as a sequence of let's say finite blowups over PL cross D. So if you're making more and more blowups, what's happening is that the number of this dual simplex is going to grow. And what you can show is that this guy is in fact the union of all these guys. If you want to write it properly, not exactly a direct limit, but inverse limit of all these guys. Okay, so I know that I started to be a bit over time. So let me think a little bit on how to conclude this series of things. So how does our proof work? Well, it exploits this this inequality here. So the proof of our theorem. So we use models. So we don't have Keller form. So we don't know exactly how to compute volumes. Okay, so that's a problem. So no Keller forms. And so what we do is we replace this by models and plus an extra. So what's the Keller form is going to be replaced by the choice of a model plus a very ample, a relatively ample line bundle over X. So I have no time to explain this, but this is, I think, the key idea. So it appears under some disguise under the work of a couple of other people. But so it's not completely clear how to define a Keller form in non-Euclidean geometry. But here, what seems to be the right analog is really the choice of some very ample line bundle over a model. And once you have this, well, remember that the Gromov argument relies on two observations. So one, the first observation was to relate the topological entropy to the growth of volumes, and then to estimate the growth of volumes. So the first thing is, well, so you construct exactly as Gromov, you look at the graph or the generalized graph of Fn, but then inside this model. And what you can show is that, so you have a model for the graph of Fn, and what you can show is that the complexity of your appends, the pullback of your chosen open cover is connected to the number of irreducible components of its spatial fiber. And once you have this, then you can use this very ample line bundle to compute, to get an upper bound of this number of irreducible component in terms of intersection numbers. And so this corresponds exactly to the second part of the Gromov argument. So you can copy its cohomological computation and conclude exactly as him that the topological entropy on the Berkovich identification is still bounded by L times lot. And it seems that I'm over time, so I'm going to stop here. Thank you very much for your attention. I'm done. Okay, I don't hear you. I'm sorry.
So, are there any questions? Yep.
I have one question, please. Are there some part of your result still valid if your rational map admit indeterminate C set, for example, isolated indeterminate C point?
So yeah, okay. So in fact, the theorem is valid for any dominant rational map.
Yeah.
Okay. So I was discussing only a holomorphic map, but the upper bound is exactly is true. I mean, Gromov upper bound is in fact a theorem for rational map. It's a theorem by Dean and Sibony.
Yeah.
And so here
in your situation is
sorry.
I mean, in your situation, is in your result, if I understand well, is from rational map, but without because the zero set of your homogeneous polynomial are zero. So it means that there's no indeterminate C set.
Yeah. So what I explained today is I assume that everything was holomorphic.
Yeah.
But the claim is that it's not necessary.
Yeah,
the theorem is actually true for any rational map.
Okay, thank you.
Yeah. Okay, so are there any more questions?
And the Yamdin inequality is not true in this context.
Okay, so the situation is much more complicated. So in dimension 1, you have a rational map defined over a non-Euclidean field whose topological entropy are equal to 0. And in fact, it's connected to the notion of good reduction. So in dimension 1, we know exactly when a map has a topological entropy 0. And what we also prove in higher dimension that a map which has a good reduction has topological entropy 0. So basically, so if you have a family of a homomorphic dynamical system, as I mentioned before, F index T defines a map over the field of real series. So the point is that if your map does not degenerate in the moduli space, then the topological entropy is 0. and we believe that the converse is true. So you don't have Yamdin inequality in general. Is it clear? I mean, I don't know.
So any more questions? No. Okay, so let's thank the speaker again.
Thank you very much.
Yeah, so the next speaker is Duc-Viet Vu. Is that correct pronunciation?
It's correct. Yeah.
It's correct. He's going to talk about complex Monge-Ampere equations in finite pluricomplex energy. So take it away.
Okay, thanks a lot. Yeah. So my special thanks to speak to the organizer for the conference for having me an opportunity to introduce my work. So this is also I worked with the Thai, as we see in the screen. So okay, let me first start with some basic notion for my talk. Okay, so I talk about first Prudy subperiodicity. So we work on firstly on the open set in Cn and use it as a C2 function. And as you know, so yeah, use is said to be the Prudy subperiodicity if you satisfy this inequality. So that means the matrix, the Hessian matrix of U is positive. Okay. So in the dimension n, so this notion is simply a subharmonic function. Okay, and nowadays it's clear that this notion of Prudy subperiodicity is a central notion in several complex variables. And one way to rephrase this inequality here is that we can write as DCU's non-negative. Here DCU is given by I over pi DDC d bar u. Okay, so here is a mistake, a typo. I should write u here. Okay. So the last inequalities allow us to define Prudy subharmonic function in the most general setting. So now we're still working on Cn, open set in Cn, and we have U now is no longer C2, but this is an upper semi-continuous function, and we say our U is a Prudy subharmonic if we have this inequality in a set of current. Okay, so here I put some more or less because the rigorous definition require a bit more work here, but for a talk, just simply think of Prudy subharmonic function as a function satisfy this inequality. Okay. Okay, so let me give some examples of PSS function. So that function, if you take a sum of PSS function, you still get a PSS function, and also you take a maximum, you still being in the same class. Okay. And more specifically, if you look at some holomorphic function on U, our open subset, then you look at the log of this kind, and also the sum of module power T1 TK here. So T1 TK they are positive constant. So this function gives you the Prudy subharmonic function. Okay, and one important remark is that if you look at the situation in a compact complex manifold, the first thing you should know is that every Prudy subharmonic function is constant due to the maximal principle. So we need to modify a bit the notion when we work on a compact setting. So we have a quasi Prudy subharmonicity. So to define it, you just look at on one form omega on x. Then we say that our function U is omega PSS if okay in bracket more or less here, if DDCU plus omega is a non-negative positive current. Okay, so this is our start. So now I talk about the main object in the talk, the complex Monge-Ampere equation. Okay, so now we have a compact Kähler manifold of dimension n, and omega is a Keller form. So we normalize omegas as the integral over x is 1. So this is not a normalization. Okay. So we look at this equation. Okay. So we call this the complex Monge-Ampere equation. So here, for the time being, U is a C2 function, omega PHS function, and mu is a smooth volume form on X of the mass equal 1. Okay, and so because U is C2, so the left hand side is makes sense. You just compute DDC by I over pi dd bar of a function, and you get DDCU plus omega. So this is the right hand side. So if you want to be more specific, you look at the local coordinate. So this left hand side here can be written as the expression you see in the slide. So here's z1 until zn, they are local coordinate on x, and phi is a Pucci symmetric function, so that omega equal to DDC phi. Okay. And the left side of our equation is just a volume form plus a function. This function is a determinant of the Hessian of the function u plus phi. Okay. So basically, this is a very complicated equation in PDE. Okay. And nowadays it was solved. We know that it was solved long ago by Zhao about 50 years ago. So Zhao solved this equation, and when mu is smooth volume form, then the solution is also smooth and PHS. Okay, and let me give some very brief history of this equation. So originally, this equation comes from the solution of Zhao by Cadoret conjecture. So we look at a complex Keller manifold, and we try to find some metric, Keller metric, so that the rigid form of that metric is given by some smooth form in the first shown class of the manifold. Okay, and more generally, if one want to find some special Keller metric on manifold, one is led to solving some Monge-Ampere type equation. I will come back to this point later in the talk, but in a moment, just keep in mind this history. And another point is that this is a complex version of some real PDE equation. So in the PDE, we also have a real Monge-Ampere equation coming from other problems in real analysis, and there are some similarity between the two equations, but in general, also we have to use different techniques to solve them. Okay. So now, this equation is solved long ago, but we still have something to do with it. And now I'm trying to explain what we can do with this equation. So there's a way to look at this equation from the Pucci potential theory. So if you look at the equation, the left hand side of the equation, this is DCU plus omega n, this left hand side. So in the previous slide, we consider U is C2. So this is a smooth form. But if you ignore the smoothness of the function, then you look at this, and this guy, we call this a Monge-Ampere operator, and this is a central object in the Pucci potential theory. So very much in the history of Pucci potential theories is about making sense of these operators. We try to define it for any U, any omega PHS function U. So this is what people are trying to do in the field. And the first thing, the first important fundamental thing is about the case where U is bounded. Okay, so we can still make sense this operator. This is due to Bedford and Taylor. Okay, and about 40 years ago. So I don't talk about the definition, but I was trying to give some information. So now you just need to keep in mind that this operators is verified for bounded U. Okay, and this is classical in the Bruce potential theory. And what's more is that even when U is not bounded, maybe U is unbounded, we can still define this operator by using this expression. Okay. So this is again due to Bedford law and also other contribution from Giorgi and these people here, Bosom and Esidier and some other. I don't cite everything, every people here. So in summary, one can define the Monge-Ampere operator DCU plus omega power n for any U in a complex Kähler manifold. So we have a name for it. This operator, we call it the non-prepolar self-product of this current DCU plus omega. And one should note that this expression is a measure on our manifold. So moreover, it is of a mass 1. Okay, so we have a measure of mass 1. So that's the last observation give us some more questions to consider in the next slide. So again, X omega is our compact Kähler manifold with omega normalized with that integral over X. And because I mentioned in the last slide that this expression here, DCU plus omega power n, so it's a measure. It's a probability measure on X. So we want to know what kind of measure it is. Okay. So we want to be more specific. We want to determine this class of measures. They are a subclass of the class of probability measures on X, but they cannot be arbitrary. So we want to know what they are. This is our aim. Okay. So here's what we can talk about U. So U here I wrote that U satisfies some regularities. So here's a list of things we want to consider. For example, you can think of the class of Monge-Ampere measure here for U holders, only holder function, or U continuous, or U boundedness, or even U has only some finite energy. I could mention it. I could talk about it later in the talk, but this is some kind of energy like EPD. Okay, and in the answer, just simply take a no condition. Doesn't mean any use omega PSS function on X. Okay, so we have a several class of measures on X, and we want to know what they are. So that's answering that question is equivalent to solving this Monge-Ampere equation. Okay, now our mu is no longer a smooth volume form, but it's a probability measure on our manifold X, and the left hand side is a non-prepolar product of DCU omega. Okay, and the first person consider this equation in the context of Bruce potential theories is Clozier. Okay, I will talk a bit about his stories in the next slide. Okay, so maybe it's before his story, I would like to give some reasons why one should consider such operators, Monge-Ampere operators, for unbounded omega PSS function. Okay, there are some reasons, but here's what I know. Okay, so first, the first one, we come back to the history of the problems of finding some special Kähler metric on a manifold, for example, Kähler-Einstein metric. And as I mentioned in the first or second slide, solving such problems once one is led to considering some complex Monge-Ampere type equation. Okay, this is not exactly the same equation, but maybe a bit modified. And usually we expect a smooth solution, okay? But the point is that there are several approaches to the problem, but one important approach is using a variational method given by these people here, and to use that method, once it is obliged to consider the class of operator here, the class of measure GCU omega, and for unbounded omega PSF function. So this is why it's important. This is the first thing, and second thing is if we go further in the quest of spectral metric on the singular spaces, okay, then the equation no longer smooth. This is what we can expect, and then in the case the solution is no longer bounded, so we have to consider unbounded solution. Okay? So this is something something come up to us naturally. Okay, and finally there's something about holomorphic dynamical system here. So if you look at a complex dynamic system, for example, a map, let's say holomorphic maps, cell map of PK is a complex projective space. Then it's well known in the field that sorry, why is it going up? A moment, sorry. Okay, so it's well known in the field that the equilibrium measures is usually given by some Monge-Ampere operators of non-smooth function. So if you look at to be more precise, if our system is holomorphic, then that's equilibrium measures usually the Monge-Ampere of some holder or continuous function, but that potential here, maybe even unbounded. If you look at some metamorphic dynamical systems, for example, if you look at a cell map of PK, but the map is not holomorphic but metamorphic, then there are some classes of which people consider in the field. They can construct some equilibrium measures of this form, but the use is not unbounded yet. So that's what. So that is some vague ideas why I am interested in looking at this Monge-Ampere equation for unbounded solutions. Yeah. Okay. Yeah. Thank you. Okay. So maybe I move on. If not. Okay. So now I come back to our equation. Again, mu is a probability measure, and u is an omega PSS function on x. Okay, so here's a list of a summary of what we know so far until now. So firstly, again, for mu smooth volume form, this we have a unique smooth solution. This is by Zhao. And if we go down a bit, if we decrease regularity, we know that the equation here admits a holder solution if and only if our measure mu is holder continuous. So this is I don't define it in the slide in the talk, but it's something like you look at the mu as a functional on the space of omega PSF function, and this functional is a holder. This is what holder continuous mean for measure. Here's a list of people contributed to the solution of in the second point. Okay, and there also we also know a lot of examples for holder continuous function. Okay, now we go down a bit to continuous function. Sorry, continuous solution. Then we know that by Closier, we know that if our measure mu is a bit irregular in the sense of capacity. Okay, so again, I don't define capacity here, but this is some kind of regularity imposing on the measure. Then we know that the equation admits some continuous solution. Okay, but this is only a sufficient condition. Okay, and finally, in the most general situation, when our measure mu is only non-prepolar, then we know that this admits a unique solution, and which is unbounded in general. Okay, and if you look at the list I gave here, the missing pieces in the list is a continuity, because here I have only the sufficient condition, not a necessary and sufficient. Okay? And also the boundedness is also not included in the list. And also the final thing is about finite energy, and this is what I will talk mostly in this talk. I will recall the definition and also to explain things around this notion. Okay, in the next slide. Okay, so here's the energy. So it was first introduced by Severino in 1998 in the local setting. So Severino solved the equation in local setting, and he introduced that notion of positive complex energy, and people later consider the same kind of energy for compact Kähler manifold, and here's so before we can give a definition, we have some observation to make. So first thing, we look at an omega PSS function, and we look at the integral of this operator. So this gives us the mass of the measure, and by some computation, we know that the mass here is less than 1, less than or equal 1. So that means our measures loses some masses compared to the classical setting. So that's why we introduce the class big E here. This is the class of a function, so that there is no loss in the mass of the Monge-Ampere operator. And now we introduce the energy. So energy is about some weight. Okay, so the weight here, the weight is simply a complex increasing function defined on the negative numbers. So this we call it a weight. Okay, and we also have some other type of weight. They are concave increasing function, also defined in the same domain, but satisfy some condition on the derivative on the growth. Okay, and so this class and class, there are two main classes of weight we consider in the literature. And here's I give an example. The most basic examples is about the minus t power p. Here p is a positive number. Okay. Okay. So I move on with the definition. So here's you see the first equation is a slide is about the energy. So that here's the way we define energy. This simply is integral over x. Okay, over x. I forgot to put the x here of the key u. Okay, and against the measure dcu plus omega n. So if this number is finite, we call it u is finite energy, finite key energy, and when we have a basic observation, is that our space big E is exhausted by the space of function with finite key energy. And this is similar to the theory of Orlick's spaces. Okay? And here's maybe it's not important for the talk, but I just want to explain why the space lower energy here is more important than the higher energy, because the lower energies allow us to treat a large class of function in a quantitative way. Okay, and also when we have a lower energy, we have the continuity of Monge-Ampere operators. So this is crucial in a pulse potential theory. Yeah, W minus is the set of convex increasing function. Yeah, I can go back if you want. Yeah. So W minus is the convex increasing function. Yeah, and W plus is a bit more complicated, but it is concave. But we could ignore W plus because W minus is more important for us. Okay. So we'll take any convex increasing function. So that's fine for us. Okay, good. So yeah, so this is point maybe we can ignore, but yeah, if you want, you can explain more. But yeah, good. Now I want to go back to the list of summaries I made before in the history of complex Monge-Ampere equation. So here's the problems people want to understand. So it's quite simple to state. So you look at the true function, omega pressure function. So that the Monge-Ampere of the first guy is dominated by the second guy. Okay, more lower constant. Okay, and we want to know that if the second guy here, V, satisfies some regularities, then we want to see whether our U, the first guy, satisfy the same properties. Okay, so this is a vague formulation, but let me go to some more detailed statement. So because that's a regularity here can be replaced by holder, continuous, or bounded. Okay, so and P can be also whether V of finite energy. Okay, so there's a list of regularities we can consider. Okay, and also if you go a bit further in the theories of closed positive current, there is some kind of statement similar to that problem for closed positive current of higher by degree. For example, if you look at the theories of superpotential by Ding-Simony, then it was proved by Ding-Viet and myself that if I don't go details, but if our current is dominated by some other current with a holder or continuous or about the superpotential, then the first current must be of the same type. Okay, so this kind of things motivate us to look at this question. Okay, that's why we want to study it. So again, as I mentioned before, that problem is still open for continuity and boundedness regularities. Okay, there was some work in the literature, but they are still largely open up to now. Okay, so again, here's a list of people contributed. The main people contributed to the holder regularity to solve that problems in the case of holder, and the finite energy, the case of finite energy, some partial case were known by Sergen and Giorgi for the weight minus T power P here. And today I will talk about my joint work with Duc-Viet. We solved that for any weight in a K minus in a W minus and W plus. So this is what the talk is about. Okay, here the statement of the main statement of our paper. So we have mu is a non-trivial probability measure on X. Okay, and we have a weight key. Okay, convex or concave. Okay, And we here's what we obtain. This equation admits a solution of finite key energy if and only if our measure mu satisfies this inequality. Okay. So this is some sort of intercommunity properties of mu. Right? We can interpret it in this way. So again a comment. So this will know for this special weight, right? That's the power t power p, and the proof cannot be extended to the general gauge. Okay, and now I will give a consequence of this statement, and maybe it's very briefly about the proof, and then I try to explain how to extend this problem to the case of big cohomology classes. Right? So here's the consequence. This is exactly the problem we posed in the previous slide. So we have a weight, okay, and we have a mu is a probability measure is dominated by some motion pair measure of finite energy. Then that measure mu must be some motion pair measure of the same kind of function. Okay, so this is a question we posed before for finite energy. Okay, good. I will try very briefly on the proof. The proof follows the usual strategy of solving a motion pair equation. The only thing new and the key thing we obtained is this inequality. That's a mixed energy estimate. Maybe I don't go into details, but the main point is that we obtain this inequality, and this is the key for our proof. Okay. This slide, so maybe I will not talk about it, but I will show you just to tell you that okay, the strategy is the same, just as other people do, but the main point is that we have a control of that mixed energy, so that's why we obtained that's a general statement, while the other didn't obtain before. This is the key I want to tell you. Okay, so maybe I move on to to big class setting. Yeah. This is a standard procedure. We use some partition of unity and some sort of configuration. This will give you that's a sequence of measure uniformly dominated by capacity. Yeah. So again, this is a standard stuff, but the new the key new ingredient is our estimate on the mixed energy. This is the point new. Any other question? Okay, I move on with a big class. Okay, so so this the setting is in this big class is more complicated because there are some other things involving in the definition. But at least I try to explain the first line. So now we have a theta is a form in a big cohomology class alpha in X, our manifold, compact manifold, and phi is a modal PSS function. Okay, I will explain about the modal. So that modal here being modal mean the volume of the theta phi. Okay, maybe I write theta phi. What is theta phi? So theta phi is the DDC of phi plus theta. Okay, so it's just the same thing. before we have theta equal to omega, but now theta is in its smooth form in a big class. And being model means we have this inequality, and also phi equal to pay phi. Pay phi is a envelope defined by this the formula. And as a matter, this requires a bit of work, but one can show that if you want to solve complex motion pair equation in a big class, also sorry, it's a mistake here. This is a DCU plus theta, not omega. If you want to solve this equation, when u here is less than theta, so the meaning is that we want to solve the equation, but the solution must be more singular than a given function. So it's just like now you have a PDE equation. You want to solve it, but not a smooth solution. We look at some solution which have some prescribed singularity. So this is what we do here. So in the Keller case, the phi is zero. So we have a number of a function which is non-negative. So this is standard. But in a big class, the new phenomenon appear. But actually also in the Keller class, the phi can be any model. So the definition may be a bit involving for you for the first time. But if you look at any function omega theta basis function with analytic singularities, they are all model in the sense given here. Okay. And for this equation, we also know that it is solved for any mu. And what's more, also we know that if mu has some good regularities and the function is bounded. So this more or less like in the Keller case. But if we follow the same strategy for the finite energy, we obtain the same result. I will show this in the next slide. So maybe you don't need to read everything here, but just to keep in mind that the equation is the last line for that equation. We still obtain a complete characterization of the class of motion pair measure with finite energy. So this is what we obtain. And as I mentioned, everything goes as it is a Keller case. As long as, this is important thing to notice, as long as one has a good enough integration by parts formula. So this is a subtle and technical part in that theory, because it's a Keller case with a bounded function. This is always true. This is classical. But if you look at the case with prescribed singularity, then the question is has some history, because because when people think of when people consider non-trivial product, that's a formula was not known immediately. Okay, this requires some little work to complete this formula. I will quickly show that statement, and I will finish my talk. Okay. So the thing you see here, the first thing, this is the standard integration by part. Okay, so you just take just like for a smooth function, they are nothing new. But as long as we move to a big class, there's some trouble coming, and the longer goes, when these people here, they consider this formula, they have to assume that this function involving in the statement here, they must be locally bounded outside some closed complete principal set. And with this assumption, they obtain the same formula. And this formula is not enough to solve the equation for general model. The most complete formulas only obtained recently in this theorem here. So there are some new notation involving here, but you can ignore this notation. Just think of it as a usual product. And we in this statement we are able to drop the assumption that our function are locally bounded outside some closed complete principal set. Okay, and this is the more or less the optimal formula, optimal integration by part formula. Okay, and this is this square here, this bracket. This is a non-trivial product. Yeah. So they in the compositing they denote they put the bracket here just to distinguish with classical case. Okay. So now we have with that formula. Yeah. So yeah, the dot is something new. I introduced it. So this is similar to non-trivial product, but with T arbitrary. So when T given by some product of closed positive on one current, then that dot is the same thing, okay? The same as a non-trivial product. But when T arbitrary closed positive current, then I put the dot here because it's something which were not known before. So just to distinguish it with other product. But if you are only interested in just T, then you can ignore that dot. Okay. So again, we have a satisfactory integration by part. Then everything goes as a calculation, and we get that characterization of measures, motion pair measure with finite energy is a big class setting with prescribed singularity. Okay. So I stop my talk here. Thank you for the attention.
Are there any questions?
Yeah, thank you. So you have a slide where you say something like the equation has a unique solution if and only if mu something maybe somewhere
okay, maybe
at the beginning.
It's the beginning,
yeah.
Okay, I will come back to that slide. Maybe this one.
Yeah, this one.
Yeah.
And then the second from the bottom. So you say it has a unique solution if and only if mu is non-pluripolar. So what if mu is pluripolar? Do you have no?
Okay. So
what
here's
happens?
So here's the answer. The left hand side is a non-pluripolar product. So this measure in the left hand side is always always charge no mass on the pluripolar set. So to be able to solve the equation, the mu must be non-pluripolar. So this is a necessary condition.
But the left hand side here you write in Not
Yeah,
this bracket, but
yeah,
this
it should
usual
be,
bracket.
yeah,
right?
it should be bracket here. Yeah, it should bracket here.
Okay, so you want to solve in for non-polar intersection.
Yeah, exactly. Yeah.
Okay. See. Yeah.
Yeah, so yeah, I should correct it here. This is a non-polar product here. Yeah, this is. Yeah.
Okay, any more questions? No? Okay, let's thank the speaker again.
Okay, thank you.
Yeah, so the next speaker is Professor Riccardo Severino. He's going to talk about the construction of the Mandelbrot set for a family of coquaternionic quadratics. So, please.
Hi. First of all, let me thank the organizers for the kind opportunity they gave me here to talk about my work. This is a joint work with some friends. We are all from the same university. And almost a decade ago, we decided to study all together some topic of mathematics that we could share. And this is the result of our work together. And well, maybe you can see that with the topics we choose were first zeros of quaternion polynomials. Then we expand to zeros of coquaternion polynomials. And then we did some work with dynamics with coquaternions. It's important to mention that for this work, for instance, for the work in dynamics, it was important to develop some software. And we have published here some mathematical tools for quaternions and also for earlier for coquaternions polynomials. Okay, quaternions, I'm sure you all have heard about. The idea here is to go and work with in the context of coquaternions. Coquaternions are very similar to quaternions, but the difference, the product is the difference between the quaternions and the coquaternions, but it is a very, very important, and that difference is very, very important. Well, I have here the idea that unlike the complex numbers and the quaternion numbers, the coquaternions are not a division algebra, and that is something that will make a whole of a difference when we study dynamical systems. Just as in the complex case, we can represent coquaternions in two ways. I must confess that what I'm going to show you is not the one I prefer. It's also not the one we work with and publish our papers. The reason for, let me show you, the reason I choose this representation is just because of I want to stress that coquaternions are R4, and it's a 4-dimensional space with obviously a certain product that I put here. But the idea, and I do this because, well, I'll just let me just finish the slide. The idea here is we are doing dynamics over the coquaternions, dynamics in the sense of discrete dynamical systems, meaning that we are iterating a coquaternion map, for instance, a quadratic map, just like that. Okay, let me just, my point here, the first part of this talk would be, I'm going to show you the following. Yeah, sorry. Let me just put here the slide with the conclusion, what I would like for everyone to feel after my talk. And the idea is that the message is that the study of dynamical systems over the coquaternions, it's wonderful. Not only by the challenging mathematics, but also for the applications. Okay, now I'm going to do the following. I'm choosing an example, a quadratic map, and I'm going to study with you the dynamics for all coquaternions. And this, now I have to say something. Because it's R4, I choose to do the following. I'm going to show you like this. I'm going to show you not R4, obviously, but R3. I'm going to, like here, I'm going to choose Q3 equal to 0. And I'm going to show you R3, the subsequent R3 has, let me say, as a movie showing planes parallel to the complex plane. Okay, first of all, let me just justify this number, this parameter choice. The idea is the following: I know that for this particular choice of the parameter, real one, the map has a real 8-cycle attractor. Okay, such that Q is the origin belongs to the cycle. This is something that if you know dynamics over the complex numbers, you'll and over also the reals, you'll okay. First of all, so I'm going to show you a movie, and the first frame is more or less obvious. This is the frame. Obvious because it looks like the basin of attraction in the complex case, the basin of attraction of the only attractor that the map can have. Please be the critical point 0 is obviously in the basin of attraction. So this is the first frame. Let me just, Q0 is here, is the X of the complex plane. Here we have Q1 is the Y, and here I have put it in here, Q3 equal to 0, just to remind you that we are trying to see this set, but only with Q3 equal to 0. And also I put it here. This is the parameter that is going to increase. And by increasing, what we are going to see are planes, are the set of the set corresponding to planes parallel to the complex plane. Okay, now I'm going to, sorry. I want to change, yes. Sorry. I have a first movie. Okay. It was supposed to begin in the beginning, but I'm already showing the movie. So in a moment, we'll see the first frame, and the first frame it will be the picture I showed you before. Okay, the first frame. And now we look at the values of decreasing values of Q2, meaning that we are going up in okay. Let me okay, that's enough. Let me go again to the slides. Let's analyze what we were seeing in that in those pictures. You can see that we have here 4 new colors besides the black and the red, and the 4 new colors corresponds to new 4 attractors of the map. And this is, I would like to stress that this is something, the idea that we can have from a quadratic map, we can have not only 1, but in this case 4, in this case 5 attractors, is something that it is part of the wonder of studying dynamics over the coquaternions. Okay, now I'm going to do the following. I have a second video for you. It's the same kind of video. I'm just going to increase the values of Q2. It's just for fun. Then I will have a third movie, and that is, it will, okay. I'll have something for you to think about it. Okay, so this is my second movie. Q2, if you can see that Q2 is taking values almost till 1.2.0, and look at this. Please be sure, please, this is not time evolution. We are seeing is, what we are seeing is it's just a way to represent a tridimensional set. Okay, this is, I think, is fantastic. Well, okay, yes. Now let me go back. Oops. Okay, now I have a third movie. And let me put it like this. If you see the values of Q2, it begins, and now it goes till almost 3.0. Okay, 2.9. Okay, it's enough, the movie, and let me go back to the slides. Okay, oops. Okay, this is a frame that I want to discuss a little bit with you, and is the following. The idea is that we could increase the value of Q2, let's say the set that we are here. This is the set, the non-black points are showing us the set of points that converges toward an attractor. And I want to just to show you that the basins of attraction are not bounded. This means that we could increase the value of Q2, and the idea is that these sets, they do not end up, let's say, the frame will not end up all black. In fact, we can, it's an easy exercise to compute too, that the red, for instance, the red one, that you can have, if you have a Q2 as you wish, it's always possible to find a point, a red point, meaning that whose mapping is going to the origin of the set of the H coq. Okay, this will be important later, but let me just show you my slides, my conclusion slide, but now with adding the idea that this unexpected richness that dynamics over the coquaternions show. So this is very, very important. This is something that will be completely different from the already known complex, the dynamics over the complex numbers that we like so much. Okay, next. This is the Mandelbrot set that everyone recognizes, and I just want to point out three known results. The idea is that a complex quadratic map has at most one attractor, which is not true anymore here when we do dynamics over coquaternions. The idea, well, this is a bad thing, that the idea that if there is an attractor, the critical point of the map belongs to the basin of attraction. This is something that this theorem and the proposition above are very, very important when you want to compute the Mandelbrot set for the complex family of maps, quadratic maps, because the first one means that you can iterate from zero, and you are sure that you'll get, if there is an attractor, the orbit of zero will be there. And the other one is even more important than the first one, because it says that if you are some distance from the origin, then you can be sure that the orbit goes to infinity with k, and this is RC. This is a constant that depends on c, but this is very, very, in order to state that it's no longer, we don't have to increase the number of iterates of zero, because you are sure that the orbit will diverge. Okay. Before this, let me show you one more video. And what I want to show you is the following. It's a rather basic video, and let me explain what we are seeing. We are just, I'm representing the existence of fixed points for the complex family z squared plus c, with c a real number. And it's a basic exercise that for values of c less than 1/4, we have two real fixed points, and then for values of c larger than 1/4, you'll have two fixed points, two complex fixed points with the same real part, and this is the graphical representation of that. Okay, I'm showing you this, and you will understand why it's next. Okay. Okay. Now I need to give you some details about coquaternions. Nothing. The first one is the conjugate, the definition of conjugate of a coquaternion. Then it is the definition of a number, the determinant of a coquaternion, and you can see here its definition. And now, and this is really important, the idea that over the coquaternions, a coquaternion is invertible if and only if the determinant of Q is different from 0. In that case, the inverse of Q can be obtained from the ratio of the conjugate of Q over the determinant of Q. Okay, the point is, why is this important? This is important because with this notion, we are going to, this notion of inverse, we are going to construct a similar, an equivalence relation in H-coq. We say that a coquaternion is similar to a coquaternion P if there exists an invertible coquaternion such that this equality holds. This is an equivalence relation. It's very easy to state it, and we are calling it the similarity classes. Okay, let me just go. The idea is the following. I just want to I want to show you what is a similarity class of a coquaternion. And the idea is very simple. If you have a real coquaternion, then the similarity class is just the set of it, just one point, just Q0. But if Q is not non-real, then the similarity class of Q is given by this QS. This is the representative of the class, and QS has these three forms according to the value, to the sign of R, being R just this quantity. This is, I avoid, this is the determinant of the vectorial part of the coquaternion, but let's just state it like this. Okay, next, I'm going to show you for non-real coquaternions how it looks. Let me just point out first that for a Q, it doesn't matter for the value of R. QS, the representative of the class, has always the real part is equal to Q0. Q0 is obviously the real part of Q. So what I'm going to show you is the following. We have here tridimensional graphs corresponding for the representation of the non-real part of a similarity class Q for different values of R, meaning that in here we are looking at coquaternions, but for Q0 equal to the real part of Q. So we have here the Q1, Q2, Q3 tridimensional representation of the class, the similarity class of Q. Okay, the point now is why I'm showing you all this. Okay, and this is the result that is very, very important for me. And the idea is the following. If Q is a fixed point of F. Look, we are here with C, the parameter C. We have quadratics, but the parameter C here is a real one. And when C is real, the idea is that if Q is a fixed point of F, then every coquaternion similar to Q is a fixed point also. Okay, this means that obviously now you understand why I show you that very basic exercise. The idea is that when C is, when we change the value of the parameter C, first we had two real fixed points of F, and then we had two complex fixed points of F. Let me go again and show you one more movie. Oh, okay. Okay. So this is the movie. As you can see, we have here the tridimensional. We have the situation, the values of C, and this is okay. I will explain later when the movie goes again to the beginning. So for values of C less than 1/4, minus 1/4, the idea is that we have two real fixed points. And because the similarity class of a real is just itself, we don't have anything but the points. And when the value of C, the parameter C goes over, it's larger than 1/4, then we know that we have two complex fixed points. And in the coquaternions, we know that every coquaternion is similar to that, to those fixed points are also fixed points. So in here, what we are seeing is that the coquaternion fixed points that emerges just because we had two complex fixed points. Okay. In the sense, what we are seeing here are the similarity classes of the complex numbers, the fixed points of the map. Okay, let me go again to the slides. Okay, but when you do the computation, when you analyze, when you study the fixed points of the family of coquaternion quadratics, when with C real parameter, you find that the fixed points of F are this situation. F1, let me put here, F1, F2, this is a degenerate situation when we have a cone, and let's forget about it. But the idea is that F3 are this is the similarity class of the complex the complex fixed points of F. So in our previous movie, we had already seen these points. Okay, now here you can see that the fixed points for C0 less than 1/4, you can see that the fixed points of F are no longer only x1 and x2, the two isolated real fixed points, but we have here also a similarity class. Look at that, this is not a similarity class of anything that we had already when we studied the complex situation. Here we are looking at the coquaternion fixed point that emerges from okay, let's see a little bit I have a third and last movie for you. Okay, is this there? Okay, no, it's not this, it's this one. And I put it, okay. Because I think it will be better if you look backwards. So the beginning of the movie is here, and you see the similarity classes we had already. And now look, when C, the values of the parameters such that the fixed points are real numbers, we have here now the representation of the similarity class F1. And the idea is that those are, if you look at you can see that the real part of those coquaternions are fixed, and well, we can, if we go back to the slides, you'll see that that what we have here. Look, the real part of all elements belonging to the similarity class F1. I'm sorry, F1 is the union of the similarity class with those two points. But the coquaternions belonging to the similarity class here, all of them have as the same real part, in this case equal to 1/2. Okay, let me just go. The idea is the following now. I'm going back to the example of the beginning of the talk, because when I show you those, when I show you the results of the study of the set, the type of dynamics that the coquaternions had for a certain choice of the parameter, I told you that we have 4 more attractors, coquaternion attractors, and I said nothing more about it. I'm going to show you something, and the idea is the following. Well, before, let me just comment in the following. A similarity class, as you could see in the representation I show you, similarity classes are sets of non-isolated points. This means that for quadratic coquaternion maps, we are no longer only with isolated fixed points, but we have now something very, very strange, very beautiful, that is sets of non-isolated points of fixed points. And the idea is that the attractors that the first map was showing us, the idea is that is the following. In addition to the real 8-cycle attractor, the map F also has 4 attractive coquaternionic 8-set cycles. And here it's important to stress the idea of sets. Look, this we have here. Well, I have here the C1, C2, C3, C4. These are the attractors, the cycles, attractor cycles, and I have here this H. All this I am going to show you are just similarity classes given by this. Okay, I'm showing you here the similarity classes for the first 3 attractors, C1, C2, C3. And I want to point out what's happened with the C4. And if you see here, C4, the attractor, is well, it is. You can see that C4, the similarity classes that compose the attractor, are only 4 similarity classes. This means that we have a 8-set cycle, but only with 4 similarity classes. And this was a little bit puzzling for us, and we suggest that well, let's say that this 8 over here, in some sense, in the origin, is the period of the points. But as I told you, it also coincides in the 3 attractors. It coincides with the number of similarity classes. But in this example, the 4th attractor, this 8 does not show us, does not tell us that 8, yes, it's the period of the points, but we thought that it was important to say that this set cycle, this 8 set cycle, was composed with only 4 similarity classes. So the point is that we propose a definition, and the definition of set cycle, we have 2 indexes, and the first one obviously is the number. No, sorry, the second one is the period of the points, but we thought that it was important also to say the number of sets that the point visits, and so now we have this. This is our the notation that we propose for a set cycle. Okay, obviously when m is equal to n, it will be better to simplify and well, let's just write Cn instead of Cn and Nen. Okay, let's go. Okay, with this new definition of the set cycle, we have also to introduce also a definition. Well, it's equivalent, a definition for the basin of attraction of a set cycle, but more important than that, the idea was the following. When we have a set of, for instance, a set of fixed points, the traditional idea, the traditional definition of attracting points is no longer it has to be modified. It's very simple to, if you think of a set of non-isolated fixed points, then if you choose one point, you can see that it's easy to see that any neighborhood that you choose will intersect the set, meaning that the neighborhood of that point will have fixed points, and it will be impossible to be attractive in the sense that the dynamics of those points will get closer to the first point. So we have a different definition of attracting set to be in accordance with the new idea of set cycles, or sets of fixed points, of sets of non-isolated fixed points. And the idea is it's very basic, let's say. The idea is that the iterates not converge to Q, but converges to a point belonging to the set S. That is the difference between this definition of attracting set relative to the traditional one. Okay, let's move on. And now I'm going to to the third and last part of my talk, and I'm going to talk with you about the construction of the Mandelbrot set for a family of coquaternion quadratics. First of all, let me say the following. We had some problems of time to work together, and it was not possible. I was optimistic, and I thought that by June we would have our paper peer-reviewed. So, because that was not the case, I had to change. It was not, let's say, it's not ethical to talk about results that were not peer-reviewed. So my point is the following. I'm going to show you the construction of the Mandelbrot set, but just the beginning of it, where the results are just very trivial, but nevertheless, we will say something about the idea, the dynamics of the coquaternions. Okay, first of all, I'm going to show you the Mandelbrot set for the corresponding complex maps. And this is the picture I want to show you. Okay, and I'm sure that you are a little bit puzzled because this is not the usual picture of the Mandelbrot set. And I have here the explanation. Yes, this is not the Mandelbrot set of the family Z squared plus C. This is the Mandelbrot set for the family of complex maps Z squared plus B times Z. Okay, so now the point is why, as you, well, okay, this is the idea here. I never mentioned which family I was talking about because I want to be a surprise. Why we choose such a family of maps? And this is very, very, very interesting. The idea is the following. Due to the non-commutativity of the product of coquaternions, a general coquaternion quadratic has the following form, and no conjugacy equivalence to a simple form is known. So what my intention to come here to talk about the construction of the Mandelbrot set for this particular family of coquaternion quadratics is clear. I want to simultaneously show you the Mandelbrot set, but also to send a message that how wonderful and rich are the study of dynamics over coquaternions. The idea that we have no longer an equivalence between quadratic families of maps as we do for the complex case, and you can choose different families, having the idea that what you are doing is not equivalent to the, in this case, to the canonical, let's say, family Q2 plus the parameter. So this is very, very important. I'm sure that I have here again my last slide, but here I underlined the idea that the unexpected richness of the dynamics over the coquaternions. Okay, let me, okay, so just for you to, this is the representation, the Mandelbrot set for the family of complex, this family of complex maps. You can see that this set is doubled here. So I'm going only to, my concern will be in here, the right one. And what I'm going to do is the following. Look that I changed the family. Now it's Q squared plus B times Q, but B now is a complex number. It is an easier problem, and it's something that would allow us to compare with the dynamics for the complex case. Okay, as you can imagine, I have here this rectangle, meaning that I'm going to show you a zoom of the Mandelbrot set, and this is only because I want to state some notation. I'm going to call the circle here C4. C4 is C4, C3, C5, and this is the Mandelbrot set for the complex map, and this corresponds to the existence of a complex four-cycle attractor for the map. This is the three-cycle attractor and the five-cycle attractor. Here I have, this is it. I should have put one here. This is the circle corresponding to the attractor fixed point. And also, let me go back. This is what I'm going to call C2. This is the values of the parameter B for which we have a complex attractive two-cycle. Okay, let me go. Okay, the idea is the following. I'm going to choose a value of the parameter B from C5. Let's go back, C5 here, and we compute the attractors of the coquaternion map. And the result is the following. The map FB for this value of B has two attractors, periodic attractors, namely one circle in some plane and five circles in five other planes. And it doesn't matter. The idea here, I have chosen this particular parameter because of the following. Look, B belongs to C5, and nevertheless, let me just put my remark. In this example, the complex five-cycle, it's no longer an attractor for F, for the coquaternion quadratic. This means that there was a change in the stability of the cycle. This is, once again, it's very, very interesting, and I'm going to show you the following. Okay, I have for you four results about the attractor. Let's see the first one. The first one says that for B belonging to C1, the complex fixed point 1 minus B is attractive for the coquaternion map. Okay, this means that the circle C1 is going to be in the Mandelbrot set of the coquaternion map F. The second is a computational result. It's very, very easy. We say that for B belonging to the circle C2, the complex two-cycle that I have here is also attractive, meaning that let's go back again. What I'm saying is that all this circle, the C1, this circle is going to belong, it's going to be in the Mandelbrot set of F, and also this circle C2. Okay, but now I have two results, two unexpected results, let's say, for you, both computational, but it's very easy because it's a negative. The idea is for B belonging to C3, the complex three-cycle of F is no longer attractive. Well, the three-cycle was an attractor for the complex map, but for the coquaternion map with the same value of B, of course, the three-cycle, the complex three-cycle is no longer attractive, meaning that the ball C3 is not going to be contained in the Mandelbrot set of that we are looking for. And the same is true for C4. The complex fourth cycle of FP is not attractive. Okay, and I'm sure that you all are thinking, what about C5? Why C5 is not here? And there is the idea is very, very beautiful. First of all, I'm going to show you, it's something that I'm going to show you the first picture we construct with the results of the following problem. The idea was the following. We compute the Mandelbrot set for the complex map, family of maps, and then we just ask for which values of B, the complex attractor was still an attractor for the coquaternion map. And the first picture we had was the following. So let me just explain a little bit. This is a real, it was not, well, the idea is that think that we painted as red points the Mandelbrot set of the complex family of maps, and then we put we painted as blacks the set of points B for which the complex attractors of F, the complex map, are still attractors of the coquaternion maps. And you can see that you can identify here C1, you can identify here C2, and you can identify here that C3 is not black. That's the result I showed you earlier. And this is C4. Yes, well, one of them. We have C4 here, and once again, C4 is not black, and that was the result already shown. Okay, let me just show you. Let me just. The idea is I'm going to show you a zoom of this part of the picture. Well, it's a different picture. You'll see the quality of the picture it's not like this. And I'm going to show you. Look at this. This is C5, and it's amazing that C5, the circle corresponding to the parameters values for which the complex map has an attractor, a 5-cycle attractor, a certain 5-cycle attractor. You can see that some of those values of B corresponds to the idea that the coquaternion quadratic has the complex 5-cycle is also an attractor for the coquaternion quadratic. And you can see here that we have a lot of red dots, meaning that, and of course, the example I gave you before was one of those red dots, meaning that for this value, particular value of the parameter, the idea that the 5-cycle, the complex 5-cycle changed stability from an attractive to non-attractive set. Okay, I'm almost, oh, it's late. I'm going back just to, it's easy to see that we have here something, but now look here, we have also something very similar to this. I have a picture for you, and look at this. Here, well, let's put again, the zoom is in this region, and the idea is that, yes, we have circles of complex attractors that are no longer, that change stability, are no longer attractors for the coquaternion map. But here, look, we have again, and here also, again, the same situation we saw for the C5, meaning that for some points of the for the circle, we have black points, meaning that for those values of the parameter, we have the complex attractor is again an attractor for the coquaternion map, but not for all. Look, this is for all the circle, but here we have points of the same circle that are not black in the sense here, in the sense that they are not any longer attractors for the coquaternion map. Okay, this is almost the end. Let me just say the following. Because we thought that it was interesting to compare the Mandelbrot set of the complex family with the corresponding Mandelbrot set for the coquaternion family. I think that the most interesting results will be if when we study the Mandelbrot set for the one parameter family of coquaternion quadratics with the parameter B in also a coquaternion. What I'm saying is that maybe the results when we choose the parameter, a complex one, are not going to be as interesting as the complex situation. I think that that is not a problem with the dynamics over the coquaternions. That is a problem because we are studying the Mandelbrot set for parameters not in H coq, but in the complex plane. Finally, let me just do the following. I have written the conclusion, I have shown you the conclusion slide, and all of them had this application, the idea that dynamics over the coquaternions are important, are wonderful, also because of the application. This is not true. It's not applications for this kind of models of time evolution are not available, let's say. And my point to put it here is the following. I think we have to work a little bit to see what to expect when such dynamics over the coquaternions can be a model of an experimental phenomena. I mean, the point is the following. We all know what is a phenomena which has a fixed point, an attractor has a fixed point. The idea is what is the same phenomena when we have sets of non-isolated fixed points. And my point is we have to study a little bit in order to give let's say the experimentalists what to see in order to see this kind of model as a good model to the phenomena they are studying. It's not trivial. I think we had to understand first before showing to the world of experimental sciences the kind of results of time series you'll get from a model like this. Let me just final this with the following. This perhaps is a little bit strange, the idea of coquaternions, but let me just say something that I should have said in the beginning. but the idea is that this is not strange at all. Why? Because coquaternions are isomorphic to the sets, to the matrices, the 2x2 real matrices, meaning that although this may be a little bit strange and cumbersome, the idea is that, well, it's not like that, because what we are dealing with here are just matrices and a very, very simple cases of 2x2 real matrices. Okay, thank you. Let me just wait for your questions.
Thank you very much. Are there any questions? Yeah.
Yes.
So I have a couple of questions. The first question is, since coquaternions are not division algebra, why when you iterate, you have not to restrict your polynomial to the points in each coq which admit an inverse? I mean, you have not to avoid the zero divisors when you iterate your polynomial, quadratic
Yes.
polynomial?
Oh, yes, you are absolutely right. Let me just say that my presentation was, let's say, a non-detailed, just an introduction to the dynamics of over the coquaternions. But you are absolutely right. You have to be careful with those points, without inverse. Yes, that's right. Absolutely true.
A second question, you have introduced over the complex the role of critical points when you have an attractor. In this case, in which sense you have critical points? Have you looked at them?
Yeah, that's a very good question. The idea is critical point is something that you in the complex case you use the derivative of the map, and here for the coquaternions you don't have such a notion of derivative of the map, so there is no critical point here, which is it's because of that lack of critical points. It is the study of the Mandelbrot set. It's very, very difficult. You have to be you have to be careful to understand the data that you get from the computer. Oh yes, that's
okay. Thank you.
Thank you very much.
So, are there any more questions? Okay.
So is there any difference between the dynamics of over quaternions and over quaternions?
Please, could you can I ask you to
okay, so you did the dynamics over quaternions, right? And now you present about dynamics on quaternions.
Yes.
So are there differences between these types of dynamics?
Yes. The differences are absolutely are giant. Let me say the following. In 1986, there was a paper about, well, let's say, about the perspective of doing dynamics over the quaternions. And let's say the conclusion of that paper was a little bit pessimistic. The idea was that the difficulties are enormous, and more or less they stated that the dynamics over quaternions would show no new things over what we knew about the complex case. In here is the difference between the difference of the product of the elements are crucial. The idea that well, let's put it here. The idea that we have here, oops, I'm sorry, that H-Coq are no longer a division algebra. It's crucial for the richness of the dynamics over the coquaternions. It's I remember that paper, they also made some conclusions about the Mandelbrot set. And I think that by that time, some people work a little bit about, and the idea was that the Mandelbrot set for the corresponding family of maps on quaternions were just like three-dimensional pictures of the same wonderful complex Mandelbrot set that we were seeing. Well, they were seeing for a few years. But the idea is that it's just like night and day. Quaternions are, but coquaternions, it's something absolutely fantastic, full of surprises. Look, I told you that families are no longer equivalent, meaning that you can choose a family and look for results. It's as simple as that. Is obviously, I try already to look for, let's say, sets of fixed points. We found lines of fixed points, not anymore, not hyperboloids, but lines. Yes, it's fantastic, but it seems that for quadratics, well, it's not, there is no more surprises. So we are looking further, and we are now studying cubic maps on coquaternions. And I can say you already that it's one wonderful world that is opening. It's absolutely fantastic.
Okay, let's thank the speaker again.
Thank you.
Yes, so the final speaker is Professor Keiji Oguiso, who's going to talk about on Kawaguchi-Silverman conjecture for birational automorphisms of irregular varieties.
Thank you very much for introduction, and thank you very much for invitations. This is my first time to come to Europe after COVID-19, and I enjoyed my stay here very much. And as the last speaker, on behalf of all participants, I'd like thanks for organizers, especially Professors Cynthia Bisi and and he's not here, Professor Stefano Luzzatto, and Professor Fei Fu. And last but probably most important, Professor Tuen Trong. Thank you very much. I already talked most important things, so please be relaxed. And my talk today is joint work. And I'm very sorry. I sincerely thanks for staff member here for perfect organization and kindness. Thank you. This is joint work with Professor Junkai Chen. type A and horseshoe 4 pin. Both are in national Taiwan University, and we make this joint work during my stay in Taipei last fall. And if you are interested in this topics, please, we already put on archive, so please take a look at the papers. And it is very hard to search Chinese name, but my name is Oguiso. This is so far only unique. So if you put my name, then automatically appear. So my talk today is everything is over Cuba algebraic closure of rational field of rational numbers. And if you like, please consider inside C. And X is smooth projective variety. And so first, F is just dominant rational self map. Then such if we given such things, then we have this is over Q bar. But if you consider all Q bar points, then because this is smooth projective, so we can recover X. And but also we consider all C valued point as explained in the talk of Professor Favre or before. And then we can consider this as a complex manifold or projective manifold. So we can consider algebraic dynamics or complex dynamics. Which is now very popular. And in this setting, the first dynamical degree, this is by definition. This is a pullback of after iteration and then pullback ample divisors. And considering exponential growth. This is, for example, as far as I know, most systematically treated by Professor Dini and Shiboni's paper are very intensively studied. And also later, Professor Chung, he gave a very purely algebraic proof. Here, H is ample. And this is also same as norm growth of this action on the Néron Severino space group. This is, if you like, this is just Picard group up to numerical equivalence. Oh, and this value is by definition greater than or equal to 1, and it is very well known that this value is strictly greater than 1 if and only if topological entropy of F is positive when this map is endomorphisms. F is endomorphism is everywhere defined. Then as today's talk of Professor Favre, this is equivalent. And so this value is very important in complex dynamics. But on the other hand, over Q bar, we consider over Q bar. So any point, this is, for example, you consider very big projective space, then any point of X Q bar, this is, I just wrote to X. Then we can choose these coordinate value inside Q bar algebraic closure, but for each value, it is a solution of some single equation with Q coefficient. So this is also inside some number field. So finite extension of Q, we may assume this. Then from this, we can also consider a complexity of point and complexity under iteration. This is this lead height function and conjecture arithmetic degree. And in my talk, first, I'd like to briefly introduce these two notions. And the interesting part is this is more geometrical. This is something more arithmetic. But these two should be related. And one of the relation proposed is the so-called Kawaguchi-Silverman conjecture, which I'll explain soon. And for example, if you consider a point in, for simplicity, P2 and over Q point, then we can write down this point as this. Oh, sorry. And these are all integers and coprime. We can write in this way. Then complexity, height of this point, this is height, value height. This is logarithms of maximal AI. For example, we have this kind of point, and this point is still not this, but this is coprime, and in this case, the height of this point is just log 3. So not so difficult. And complexity means if coordinate value is bigger and bigger, then point can be considered more and more complex. Later I say some comment, but this is just a Q point, so we can define in this way. But if we consider that kind of arbitrary number field, then this is quite difficult to generalize as it is. And So, but this part, this value is considered as log 2 minus 1. And this is multiplicity of 2 of these numbers. Then this is equal to log 3. And this part is just the number of this prime field. And if we consider in this way about height, then this can be naturally generalized. And for but first choose K number field such that K. Then we define height of this point as first divided out this, and then we run through all places. This is infinite place. Infinite place. Sorry. Infinite place and also spec. Okay. And then we take log max AI so and consider this value and run through all places, and this is height values, and of course this is if Archimedean part, then this is just absolute value under embedding, and this part is just like P and minus order of AI. We take like this. This is exactly the same way as this. And then if we define like this, then this is well defined. It is known that this is well defined. And actually, well definedness is two sense. We have ambiguity of the choice of field K, but this value does not depend on this ambiguity of field. And more important for us, expression of this is not unique. So we can multiply, but also does not depend on how to express this. So this value is, then we can choose one coordinate, just one. Then this is just always non-negative. And this is a height function. But and for lateralism, I consider +1 is just maximal of this, and then F is dominant rational map, and we choose this locus is that point X such that never enter indeterminacy locus. Locus of F. Then for all point, I should emphasize this is all inside Q bar. And if we take such a point, then we can freely compose. We can freely compose. And this alpha F X, this is defined H plus, and considering orbit behavior and how complex to this point under this measure, and then taking exponential measure of this. This is so-called, this is a arithmetic height. But here there are two problems. First problem is this is countable set, because Q is countable, so points are countable. But this condition is again countable condition. So usually this could be empty, but there is a result of Americ that F is then this is actually dense. So first countability problem is okay, but most major problem is this is existence. This is still open problem. Where? Order. So just finitely many, non-finite. Then and one more problem here. I'll return back to later. This is we use one height. Height is defined for the point of Pn, and we have embedding. So for each point we have height, but there are a lot of embedding. Even if for the same place, even if to put for the same place, we have, for example, this point can be replaced by this point by PGL action, PGLQ action. So, but then height is this height is 0, but this is log 3. So height is not intrinsic in this sense. So, in order to overcome this difficulty, this part, and also as a good tool, we later introduce value machinery. But before it, let us give some examples to as feeling. Was to this map I took from Silverman's paper, and in this case, the indeterminacy set is just become all 0. So this is 0, 1, 0, 1, 0, 0. And P2 minus P2F. So this is at some step map cannot define the locus. This is just 0, x0, x1, 0. So most point is defined. Now, let us consider what is an iteration. Then this is a very beautiful form. I'll explain later. An x2 an dot x0 an x1 an plus 1 and x2 an plus 2. This is at least I found in his paper. And here this number is nothing but Fibonacci sequence. And from this expression, we compute dynamical degree. This is so pullback of so anyway, this is Fibonacci. So this degree is by this relation n plus 2, and this is also total degree is n plus 2. So this is fit well with expression, and then this is nothing but pullback of hyperplane and intersection with hyperplane. So this is just degree n plus 2 and limit just degree gross. So and because this is Fibonacci, this number is easily to compute like this. I don't write down that this is looks like of course we can write down exact formula, but so we have this. And for example, if we choose point 1, then how about this? In this case, because you can see from this, FNP is always 1, 1, 1. So this is H plus. This is by our definition. This is 0, so this is 1. This is maximum. That value is 0. So, but we make But for example, previous point, Q, then what this? Maybe this is something 2an plus 1, 2an, 3an, and 2an, 2an plus 1, 3an plus 2. So max x0. Sorry. You are right. This and this becomes n plus 1. Thank you very much. Minus 1. Looks like this. So maximal one is this. So this is log. This is again looks like this is an plus 2. And for the same formula. And if you play this kind of games, and if you choose point randomly, then almost all point you can find, yes? No. Third coordinate is always just 3. Second one. Q is this is FNQ. No. This is I enter this problem later, but here we have no, because this and this has no common. Q, 2. Sorry. Thank you. Yes. Yeah, and Kawaguchi-Silverman's conjecture is like this. Is X is defined over Q, smooth projective, and F is self map. Then first one is for all F exists. So this case it exists, but this is still unknown. And second one is relation. And if Zariski dense, this is X is of course. Then this is equal to the first dynamical degree. These two are the conjecture. So second conjecture is if we take enough general point with respect to this action, then such a point height function recovers dynamical degree. And so this is something very interesting, suggests some very interesting relation between arithmetics and geometry. So some people studied this, and I'm also interested in this problem. So, and I enter. I wanted to study more about this. And very important remark is first, this is Silverman, Kawaguchi-Silverman. They first claimed, but this is so-called epsilon delta, very complicated epsilon delta method. And in epsilon delta method, dependence of the constant very delicate. And they made some mistake in this aspect. But later, Matsuzawa correct this. And we don't know this, but if we consider limit soup, this we can always consider. Because this always exists. In a priori might be infinite. But then, sorry, this is, I put this. Then at least we can say upper limit is governed by first dynamical degree. This is one of the most fundamental results and in this area. And also for one, if F is everywhere defined, then exists. This is known result. And for second case, not much is actually known. For two, maybe most remarkable, one of the most remarkable result is that if A is a abelian variety, then 2 is okay. And in this case, abelian variety contains no rational curves. So every rational dominant map is endomorphisms. And endomorphism is not only as endomorphism of abelian variety, but also we have some translation. Both cases, this is known. This is Kawaguchi. And also Silverman. And secondly, curve case, it is trivially hold. And X is surface. I should say this first. in this case, 2 is also okay for all rational map except S is P2. And P2 case is most difficult, even for F is birational. And finally, surface is quite close to hyperkähler manifold. This I don't define. This is a kind of generalization of K3 surface, and F is odd. Then 2 is okay. This is Kawaguchi, and later Matsuzawa, Shibata, Sano, and this is Ultra and Professor Satorian. And so from this picture, surface case, because we can take minimal model, then most cases we can reduce to minimal model and automorphisms. But birational automorphism case, almost nothing known. And another things I'd like to discuss is for 2, there are two issues. First of all, if dynamical degree is 1, so this is mild, then we have this is by this one, and but because we take this is limit inf, because we take maximum of 0 and 1, so this is always bigger than 1. So all equal. So and so this case some kind of trivially hold. So this case is not so much interest. And another thing is that is a point of x such that Zariski dense. We consider this set, and if this set is empty, then this statement is nothing, because assumption is false. Then 2 is vacuously hold. Vacuously hold. So it is also interesting part is really we have really get cases where we have Zariski dense orbit or not. This is also important. Otherwise, problem is empty. And and we also would like to study this part, and our main result is about also and also when empty. We would like them as somehow meaningful, and sorry. Probably this is very spreaded branch of participants. So I should say, in order to study this, there are several viewpoints. Just intrinsic characterization with respect to f and x. This is one way. And there is some Zariski dense orbit conjecture in this term. Another thing is that because I'm algebraic geometer, birational algebraic geometer, so what kind of invariant we can expect this. And in this view, most basic invariant of X itself is, first one is Kodaira dimension. This is maximum of dimension of image. This is pluricanonical map. So Kx is just wedge product of cotangent bundle. And this is minus infinity if there are no members. This is Kodaira dimension and very important invariant. And next important invariant is irregularity. This is irregularity. This is by definition. I think this definition is more closed. This is a dimension of one Holmes, And actually, importance of this is, then we have Albanese map goes to this is abelian variety. This is the Albanese map X. And if tensor C, this part is divided out H1 free part. Usual torus, and map is just X goes to omega, X0. X omega, evaluation of one Holm. And the result, and these two are both are birational invariant, and algebraic geometry first classification, we look at first Kodaira dimension and then irregularity, and after that, there are several invariants. For example, surface classification is done with these two invariant. And our result is in this direction. CLO. Junkai Chen and Professor Lin and myself. So S is the set of minus infinity 0, minus infinity t minus 2, minus 1, and X is I assume and 0, 0, 0, d minus 2, and 0, d. And here, this is removed. I put then first, if with so we have Zariski dense orbit point, then Kodaira dimension and irregularity of X must be necessarily inside this set. This is the first result. And this is the first statement. And second statement is conversely, for all in this range, there exists X of dimension D and such with automorphisms with at least one dense orbit point, and also entropy. This is the same as after complexification entropy positive. So, in birational geometrical sense, this range of manifold in this range are meaningful to consider Kawaguchi-Silverman's conjecture too, because otherwise either vacuously fold or trivially hold. And this is first result. And second result is we check this for threefold case, and X is a smooth projective threefold over Q bar, and then first of all, conjecture 2, I wrote KC, hold for, sorry, most important things is now we assume irregularity is positive. So just this part, hold for if F is automorphism and threefold positive irregularity, then we can prove Kawaguchi-Silverman's conjecture hold. And I'm more interested in birational automorphism because very few results, and hold for F will X if X is not covered by rational surfaces. So we have no dominant map from families of rational surfaces to X. If this is not this case, then we can show that this also hold for birational automorphisms. And now time is yes. In this case, and finally, I just say few words about the proof. And for one, first of all, this is image. In this case, all birational map induced this automorphism coming from PGL, and this is finite group. This is by Dream, Nakamura, Ueno, classical result. If X is F is birational, and also Nakayama san, if F is arbitrary dominant rational map. And our case, this is enough. So if then this dimension is bigger than 1. So this must be empty because essentially fiber is preserved because finite order. So considering kappa 0 and minus infinity is important. And construction of examples, we use pivot unit. And just one excluded case, this we use Phybeck's solution of -1. This is slightly technical, so I omit to tell detail. And lastly, most important part is that we reduce to change. This is for theorem 2 to change model to make to equivariantly. This part is most essential part for for us for our result. But actually, if we would know question. This is generically finite or just birational. In this case, Kawaguchi-Silverman's conjecture for if this is under equivariant setting, if we can reduce Kawaguchi-Silverman from top part or bottom part, then we can get more result. And actually, this just birational is quite useful. This is my impression. And this is looks technical, but quite important question, I think. And this question, I think, very fit well with dynamical degree Professor Tim and Professor Nigen and Professor Dini proved. Fx, Fy, pi pi, and this is generically finite. Then sorry, I'm sorry to abbreviate your name. Generically finite morphism dynamical degree does not change. And if Kawaguchi-Silverman's conjecture would true, then I think similar picture should hold. So this can be expected, but actually, what we can prove is that with some condition, like this is automorphism and so on, then somehow we can prove what we need to prove this theorem. This is our result and very brief outline of sketch of proof. This is all. Thank you very much.
Yeah, any questions? Can you just go back to this thing here for proving theorem one? How I didn't quite see how you're giving the existence of a birational map. Is that right?
This
Yes. Is that what you're doing? I didn't quite see why you were getting a birational map.
Sorry. This is, for example, assume we get birational map F is given.
I see. I'm sorry, I misread your theorem. So you're saying, so in your theorem one, you're not saying there exists a birational map. You're saying if there's also
yes. Then yes. Then
okay.
F automatically induce PGL action.
Yeah,
so
okay.
image this action induce action on the image. This is necessarily finite. This is the result of this, and this use Hodge theory. Okay. But we can just prove after tensorizing C. So this is no problem.
Okay. More questions?
I have two questions. The first one is a sufficient condition, a very practical sufficient condition to ensure that the set ZF is non-empty. This is
this is
Z orbit density.
This is very I don't know practical or not, but very natural conjecture about existence of Zariski dense orbit is the following. This is also conjecture. This is enough. This is anyway conjecture. So here's Zariski dense. If and only if there exists some. So, in other words, there exists some non-constant invariant rational. This is, of course, if we have this, then here's no, sorry. sorry. So this is, if we have this situation, then clearly this, because fiber is preserved. Orbit become inside fibers. But from here to here is unknown. But this direction is important direction. But we forgot this just some field K. If K is uncountable, I think we just use uncountability and countability of Chow variety. So maybe this is not needed, but for safety, I put this. Then this direction is okay. So for example, over C, this is true, and this is Campana, American Campana.
Thank you. And my second question is that you have the first dynamical delta 1, and then you have the arithmetic. Your version is alpha f, and if and you have also we can imagine we have also the second dynamical delta 2, and what is the analog arithmetic analog of the height? What in the
yes, this is studied by Regiutra and also other people, but I did not follow this. But there are some trial.
Yeah, thank you.
Maybe interesting because. Sorry. Higher dimension, higher dynamical degree.
Yeah.
That can be applied some geometry. Later. So.
Yeah. Sorry.
We use your and Tuyon's result about the relative dynamic degree. So because if you consider arithmetical higher arithmetical height, you should consider a model. So you are in the relative setting, and then this higher arithmetical degree will be bound above by maximum of 2 dynamic degrees, not just 1. Yeah. So if for points we consider number 1 and number 0, but number 0 is just 1. So then this is kind of a generalization of Kawaguchi-Silverman conjecture for higher arithmetic degree.
Thank you very much.
Yeah. So more questions? No? Okay. So let's thank the speaker again.
Thank you very much. Thank you very much for attention.
Yeah, and I would also like to add my thanks to the organizers. So this very interesting conference and for an excellent choice of location. And also to the people here at the Skola Normale who has made everything run so smoothly. So I suggest we give them all a hand.